Good morning, everyone. We're going to start now for a full day, and please remember, of course, tonight at 5:30, we're going to have a poster session with drinks and snacks and lots of good science talk.
Okay, good morning, everyone. So I hope you're doing well. Let's begin and continue the session we began yesterday about early Mars environment, inputs from mineralogy and sedimentology. And we are going to begin the session with Jérémy Brossier on deciphering Mars early aqueous environments using ferromagnesium clay diversity across the crystal dichotomy.
Okay. Hi, everyone. For the moment, okay. No, sorry. I just wanted to verify if everything is working fine. So, in this presentation, I will introduce you the work that I've been doing those few last year, like starting with the exploration of Oxia Planum, the selected landing site for the Rosalind Franklin rover, in context with the ExoMars mission. So we are part of the MAMIS team. So here I came today to represent this team and the work that we have been doing from the analysis of the orbital data. So the thing here we focus on the ferromagnesium clays, as they are like the main, let's say, mineralogical phases found on Oxia so far. And also they are supposed to be one of the prime targets for the search of life on the planet. So as they are made under conditions that are in favor for the emergence of life, and they are known to trap and preserve those biosignatures, organic compounds, over time. So the idea here was to collect maximum of data to retrieve those ferromagnesium clays, so their signatures, let's say. So for this we use the CRISM data. So CRISM is now retired, so we have like no more new data, but we still have a lot, like a ton of data to use and investigate. So what we did is like the usual pipeline, you know, like the pre-processing that we do, and the calibration, the correction, etc. And then we have this denoising, which is very important to add, because the problem with CRISM is like most of the data are like very, very noisy. That can be a nightmare sometimes. So here is an example with 3 different cubes that I have collected. Like for instance, on the left you have McLaughlin crater, which is a large crater near in the Marsalis area. You have in the middle 2 small craters within Marsalis area, in which the clays are found in the inner rims as well as in the ejecta. And then on the right you have Nili Fossae, like a very nice outcrop there. So here you have on top the RGB composite, so you can easily recognize the ferromagnesium clays as being like kind of green yellowish. And then in the bottom you have the index. So because to find those clays we need to have an absorption at 2.3 but also 1.9 and other additional band I will talk about. And then on the bottom is the ROI, so like we define the ROI, so we map those clay bearing outcrops, let's say. So by looking for those clays, we end up by doing this kind of survey, in fact. So while looking for them, we also find other things. So instead of just ignoring those cubes, we just reported them in a map. So we find also some aluminum-rich phases, especially like in Marsalis, for instance. You also sometimes have chlorides, like in Tyrrhena terra, and so on. Also sulfates, as well as together with like clays, like in Meridiani Planum and stuff like this. So this, as most of you already know, especially for those who are like manipulating those spectral data. So like zoom in, because the point here, the initial idea was to compare Oxia Planum with its neighboring region, so especially on the Circumclis Planitia, to keep it in a context with the ExoMars rover mission. But then we started to include also some data in Marsalis and then on Nili Fossae, because those are like 2 places where we have like a ton of data, good quality data, because they were supposed to be the prime target for the nominal mission of MRO, nominal phase of G0 mission. So this is where like you have the best data collection, let's say. And then we started to look a bit more to this. So, and then it ended up like a survey, like you could see already in the literature from John Carter, like Carter et al. 2013, updated in 2023. but also from Hellman and Edward in 2014. So my point here is just I focus on the ferromagnetic clay. So I took all those kind of, I think it's like more than 800 cubes with, let's say, certain, how can I say, like, where we clearly identify them. So just a little overview of the regions that we are like covering with this kind of survey. So you have like the Marsalis area. As you can see, you have a lot of data, and especially targeting those clay-bearing outcrops known from the literature already, because Marsalis is a place that has been studied a lot of time. You have like a lot of papers about this. And Auxia, which is not shown here, but is more like southwest. Already where the mineralogy has been already more or less studied, let's say, from Lucia Mando in 2021, by myself in 2022, and then Joseph McNeil lately, but focusing on the hydrated silica found near the delta fan-shaped deposit, let's say. So you also have Nidiphosae, another place with a lot of like a huge mineralogical diversity. Also a lot of carbonates has been identified there. And then also Libia Montes, another place of interest. And then other places, like also we have here like Gale Crater, where you have like clays and sulfate, but we already discussed about those yesterday. So here is a few examples of spectra that I have obtained from this survey for the ferromagnetic clays, where we see absorption in 1.4, 2.3, 2.4, like those characteristics of the ferromagnetic clays. And we see variation between them. Those variations are kind of recognized easily, and also they help indicate some changes in the relative abundance between iron and magnesium in the clay structure, but as well as the iron oxidation state, which is also something very important. And we also observe a band at 2.5 that could be due to carbonates, as something that we already suggested in the case of Auxia planum. But the thing is, this band is relatively recurrent. I will talk about this at the end. Okay. So, and on the right, the plot on the right is like analogs. Usually, we always compare with like saponite, like for the magnesium-rich clay, smectite. Then you have also neutronite for the iron-rich, and the intermediate phase. I will always use the term intermediate phase, but here I think about the vermiculite and also the ferrosaponites. So, for instance, the work that we are also doing the point is, like, for every outcrop that we have, we try to assign a specific compositional trend, nature. So for that, for every ROI that we have, for every outcrop, we try to extract, for every pixel, like a minima, like a fit. We create a fit to extract the minima, so to have the exact band position. And so we have this kind of quasi-statistical approach, let's say. And so here the example with Marsalis, where we try to extract this exact band position for the band at 1.4, 2.3, and 2.4. So for me, like the three key absorption for that define ferromagnetic clays. In which we have, in the case of Marsalis, we have a band centered at 142, 229, and 240, which is characteristic of the neutronite on Mars. On the opposite, you have Nidiphosae here, where you have the band at 140, 231, and 239, which is characteristic of the saponite. So the point here is to use to combine those three different bands to assign a specific compositional trend, and we did it for every outcrop that we reported here. With the exception of some of them where that were too noisy, let's say we could not clearly define an outcrop, so we could not take the risk to do it. So it's not applied. So we did it for all let's say, this is an example with the major regions covered by this survey. So you retrieve Marsalis with its known neutronite clay, let's say, trend with one observation that is actually more intermediate phase. Then you have like Nili fossae, in which we have like a bit more of variability, intermediate phase, and a lot of saponite also, and a bit of neutronite. Libya Montes, more or less the same, but with a lot of saponite. Meridiani Planum with a lot of neutronite and a lot of intermediate phase, and so on and so on. Gale Crater, a lot of neutronite and a few intermediate phase clays. This is consistent with the literature also, J02, and then Oxia Planum, in which here I have incorporated like 2 cubes in the Oxia Planum, like where like the rover is supposed to land, more or less, and then the catchment where you have neutronite, and then you have sequences more similar to what you have in Marsalis, and this will be discussed in more details by Ines in the next talk. So I will not go in details on this. So this we can also convert it into a map, and then you can recognize here like the dark blue. You have the neutronite of Marsalis and the plateau surrounding Valles Marineris, consistent with the literature. You have the light blue, where you have like the more intermediate clays, like ferrosaponite, vermiculite, that are like kind of dominating the outcrop, let's say, the population of outcrop I have, and a few saponites here and there, like for instance in Tirrena Terra. So yeah, so this is just to zoom in. So yeah. So sometimes you can also say, like for instance, Marsalis with essentially neutronite. You can say Martian, Marsalis-like clays, and Oxia, for instance, with intermediate phases. So also with this methodology that I use, we are also able to recognize some intermediate, some double trends sometimes. For instance, in McLaughlin Crater, you have like a neutronite next to saponite, same in Nili fossae, and this could be due to a different weathering condition, or maybe like one outcrop has been exposed earlier than the other, and then you have like you leading to these different trends, and so this shift in the band absorption. So this is what we have for both regions, like the cube in McLaughlin Crater on top, and on the bottom you have. And you clearly see the difference. For instance, in the middle, you have like the 2.3 absorption. You have 229, 20, 28 on top, which is dark blue, and then light blue. I don't know if it's clear from here, but and then you have a light blue for the saponite. So the same for the 2 other bands. It's working pretty well there. So I wanted also to say a few things about the possible carbonates. The thing is, now the work will be to focus a bit more on this possibility that because like carbonates may be more present than we think, and they are like just hiding amongst the other phases like clays and sulfates and stuff like this. So because we already have a few detections of those carbonates on the planet, like from Bethany Hellman already in 2008, and then through the rover in situ measurement, and we think that they are like more ferromanizing carbonates. And the point here is like, since we see this band at 2.5 everywhere, the point will be to explore a bit more this possibility, this hypothesis that those carbonates may be mixed with clays. I'm not saying that they are formed together, but maybe they are present there. And for this, we will need to investigate a bit more this absorption at 2.5, and maybe explore also the spectral signature beyond the 3 micron range, which is like from 3 to 4 micron range is a very hard and challenging spectral range to understand, but still we can see a few things. So this will be for the future. So I wanted to finish with this, in fact. So the point of doing this characterization is like, now that we have identified and characterized a bit more, I think it's very important to corroborate this work with what is being done in the lab. For instance, the test of the capacity of those different clay to preserve the biomarkers over time under, for instance, thermal degradation and stuff like this, or oxidation. Like a few work have been done already, from modeling to lab experimentation, showing, for instance, like the neutronite, which is rapidly formed under oxidizing condition, for instance, will not really be good into preserving those biomarkers over time, something that was already said by Seth Gainey in 2017, and then later in 2022. But then I see that I am a bit late, so I will just move on to this. Now we are also looking for like field trip in Italy to look for analog sites. And today my colleagues are actually in Solfatara di Pomezia to look for additional clays. So I'm sorry, I went a bit too slow, but
Thank you, Jeremy. We have a couple of minutes for questions.
Thank you very much for this nice talk. I have a very naive question. Do you, among all the mapping you do you silicate clays that are really not in ancient terrains, for instance? Do you see clays that would have been transported covering glaciers or something like that? Or it's always on the ancient bedrock?
so far it's always on the ancient bedrock, yeah. Like it's from like Noachian to maybe at best early experience, but I didn't see anything related to ice so far in this survey at least. Maybe someone else finds something in their own work, but not mine.
Question on from what we've learned at Gale, the fact that we know the amount really strictly in Gale for X-ray diffraction, the amount of clay post-rock. But from orbit, we see a different story. From that perspective, do you expect, for instance, in Oxyaplanum, from the mapping of the texture, even if there is no clay signature, put reasonably a clay signature because similar outcrop has a definitive signature? So the fact that the signature is patchy from orbit, how do you interpret that?
I didn't understand the question, but
the fact that the signature, the orbital signature, does not relate directly to the composition, as we learn in Gale. Can we use the mapping from the texture to infer the wider distribution of clays in Oxyaplanum or places like that, just based on texture?
Maybe I understood, but if you compare with other kind of data sets, maybe for the texture, like iRise or Cassis and stuff like this, you can expand the mapping of the clays. I mean, people are already doing it, I guess. Also, not only for the clays, but also for hydrated silica and other mineralogical phases. It's possible. Some people, I guess, are already working on this.
How it would change how each clay type is represented. That expand on, for instance, saponite. Expand on.
This then I cannot. I'm not sure we could differentiate this compositional nature. In fact, no, I don't think so.
Okay, thank you. Thanks again, Jeremy. So next speaker is Ines Torres Aore. She will speak about Noachian Mars clay continuity between Oxyaplanum and Mars Valles.
Good morning, everyone. So I'm Ines. I just started my third year PhD in Lyon under the supervision of Cathy, Quentin Nataf, and John Carter. So today I'll be presenting a study that has just been submitted, which is a study about the clay continuity between two major Noachian sites, which are Oxyaplanum and Mars Valles. So first, a bit of context. So we are looking at the Chryse-Planitia basin, and here we have the dichotomy margins, where you can see the detections of iron magnesium clays, and these are the clay detections we are interested in this study. Sometimes pixels are sparsely distributed, especially on the western margin, so it can be hard to know exactly what is their geologic history and if they have some kind of a subdivision. So we focused first on two major sites, which are Mars Valles and Oxyaplanum. So both have been studied for a long time now, and Oxyaplanum is the landing site of the future ExoMars rover mission. So a word about the age of these deposits. So when we talk about Oxyaplanum and Mars Vallis deposits, it's actually the oldest sedimentary deposits on which a rover will land, so especially for Oxyaplanum. So in comparison, you can see the age of other sedimentary deposits studied by other missions in situ. So about the clay, so there's a very dense bibliography on Mars Vallis clays. So I will be focusing on the basal stratigraphy of Mars Vallis. I'm not focusing on the top of the pedogenesis sequence, but on top of it you have aluminium-rich clays, which are mostly consistent with montmorillonite. And at the bottom of the clay sequence, it's mainly nontronite-rich units. I think there's no pointer, no? Or maybe I can do this. Ah no, pointer. Okay, like this. So yes, so the basal clay sequence is the one I'm interested in Mars Vallis. And for Oxyaplanum, we have this widespread also iron magnesium deposit, which is this red layer that drapes all the topography, and it's mostly consistent with vermiculite and saponite, so iron 2+ magnesium rich smectites. There's also later aqueous history with the delta catchment, but I'm not focusing on this part of the clay sequence. So now let me show you some spectral maps and texture study. So we are back in the dichotomy margin with Mars Vallis and Oxyaplanum. And when we took the detections from the MOCAS catalog, we masked all the aluminium-rich clays. And with this study, we developed new spectral criterion that allow us to clearly distinguish two spectral end members. So the first type of clays is what I call the OP type of clay, which is mostly magnesium-rich smectite or vermiculite. So you can see in the spectra then big ferroslope and also the absorption at 2.3, which is shifted to longer wavelengths for more magnesium absorption than iron. And the second end member is the MV type of clay, iron 3+ rich nontronite with absorption at 2.29 and also a slope after 2.2. So omega is great because it has a great spatial extent, but then we also have a lot of mixing for each pixel. It's between 300 meters to 5 kilometers for each pixel, so we need to check at higher resolution. So we added CRISM mapping to this study, and here you have a summary of all spectral observations. So what we see is that we distinguish the little red circle, which is OP type of clays, everywhere in Oxyaplanum and in the Mars Vallis region, and we distinguish MV type of clays in all Mars Vallis region and in the Oxyaplanum region right above delta catchment elevations. So the delta is here, and from here northwards it's downslope. So starting from here, we don't see any more MV type absorptions. So I will just show you two examples, one in Mars Vallis and another one in Oxyaplanum, of what the mapping looks like. So I use CTX elevation, then high-rise, and the CRISM, where I mask the aluminium signal and pyroxenes. And this is the result of the combination of all spectral parameters. I won't get into the details, but you can ask questions later. And when we add the high-rise imaging, we can see that variation in composition actually appear as color and texture differences with the high-rise. So here, for example, when we zoom in, we have this very bright nontronite unit and then the brown pinkish OP-type units. And what we found is that there's also a cratered paleosurface right at the limit between the two units. So here you can see it's infilled with it's a paleocrater infilled with a brighter unit. So on the left, we have a good example of a paleocrater, and on top of it, we mapped our spectral parameter combination, so it works pretty well to distinguish both type of spectral end members. We built cross-sections, so this is just one example of this cube, where we also mapped aluminium-rich units and capping units. And so the cross-section looks like this with a basal OP-type unit, and right at the limit with the upper blue unit, we can find paleocraters. So this paleosurface is interpreted as the top of the OP-type unit. Another example in oxyaplanum. So here, the mapping of a combination of parameters with CRISM also leads to two spectral end members in red and blue. And when we zoom with HiRISE, we also have this, at the very limit between two units, this paleocratered surface. So there was a depositional hiatus between the deposition of OP-type clays, then the paleosurface that got heavily cratered, and after that we had the deposition of MB-type clays and above. So we did this clay texture mapping in the whole region from Oxia to Mars valleys. So the mapping looks like this for Oxia type of clays. We have a sort of pinkish fractured with 10-meter spacing fractures, and then for Mars valleys type of clays, we have a yellow non-tronite rich unit, sometimes with blue patches for what is interpreted as aluminium units. And also we have many craters with layering and different colors in the layering, so here could be one interpretation of the stratigraphic log. And what's important here is that same for the clay texture mapping, we don't find MB-type textures below the delta catchment elevation, but we do find OP-type textures everywhere in oxyaplanum, in the plateaus between the two sites and in Mars valleys. Okay, so I wanted to take some time to discuss the implications of these results for Noachian Mars. So one of the interesting results with this mapping spectral and textures is that we can do a plot with the elevations at which we find OP-type signatures or MB-type and the paleosurface texture. And actually in Mars valleys, the plateau we were studying is at lower elevation than in the oxyaplanum region, and we find this kind of plot. So in Mars valleys, we find deposits all the way down to the top in the plateaus too, and in Oxia we have no evidence of the MB type of clays below delta catchment elevation. So here something happened, and that's a question. Did MB type clays ever deposited on top of oxyaplanum? So there are different hypotheses. One could be that first they indeed deposited on top of oxyaplanum, but then they got eroded. So either they completely disappeared, they were completely eroded, and that's why we don't find signal for now, so we still have to investigate a bit more. And maybe they got deposited, but then there are still some signs of a signal. The second option would be that at the beginning, MB-type clays actually never deposited on top of oxyaplanum, so it could be due to environmental controls, such as limited oxidation, for example. I'll talk about it later. Or it could be also burial conditions, maybe at the time when the MB-type unit deposited, oxyaplanum was under a capping unit, an old Noachian capping unit, or maybe underwater, or maybe under ice cover. And the third hypothesis could be that the same protholith then altered in different ways, but the finding of the paleosurface disproves this hypothesis because we have a clear sedimentary hiatus between the two units. So I think we can rule out this hypothesis. Here's a proposed sequence of events. So first, the oxyaplanum type of clay deposits everywhere, and then there's a sedimentary hiatus with a craterized paleosurface forming. A first option could be that MB-type deposits everywhere. Then we have leaching processes and erosion, then a capping unit. And now what we see is the product of almost 4 billion years of erosion. But there are other hypotheses, like Oxia being buried under another unit, or also maybe there's differential erosion, because Mars valleys could be protected maybe from erosion. That's why we do see at lower elevations still Mars valleys units, but not in Oxyaplanum. So here I try to draw Mars valleys on the left side and Oxyaplanum with the delta here on the right. So some geochemistry implications. What we found is that Mars valleys type of clays and aluminium clays are found in association, so they must be genetically linked. So also other hypotheses, maybe Mars valleys was a volcanoclastic origin, so perhaps it was during an intense volcanic period with increased greenhouse effects that promoted the leaching of aluminium silica phases. What we observe is that OP-type and MB-type of clays are not found in association, for example, at Oxyaplanum, so it must be two distinct alteration events. So about this difference, maybe it's a difference in environmental conditions. So one example could be that OP-type clays formed under more reducing conditions. Then we had a sedimentary hiatus, long enough to craterize heavily the surface, and later MB-type formed maybe during more oxidizing conditions. So is this an evidence of a gradual atmospheric oxidation? Something to investigate. So when we think of the origin of Oxyaplanum clay deposits, could it be lacustrine deposits? Well, we saw a widespread deposition alteration event, so I think we can rule out this hypothesis. Could it be marine deposits? Well, if they are deposits, then it should be the oldest Arabia Terra shoreline because it goes way high in the plateaus. And then it would be followed by an ocean retreat for the paleocrater surface to form. But we should resolve elevation inconsistency because we find Mars valleys clays at lower elevation than Oxyaplanum delta catchment level. It could be paleostrine deposits on the margin of the dichotomy, maybe subsurface alteration, but with the paleosurface, it's kind of hard to believe this hypothesis, or pediments in arid climate. So here are some hypotheses. Okay, so I will leave you with these take-home messages. We managed to find, to develop spectral criteria and also corrections for our cubes that allow us to distinguish two spectral end members. If you have to remember one thing, is this stratigraphic log we found with a paleosurface marking a sedimentary hiatus in the early Mars history. And Oxia-type are widespread, so ExoMars will try to answer the question of it.
Again, with the torrential hot rains actually causing the alteration?
So I think one thing that is important also, I will try to go to the story here. So you talk maybe about the first alteration event at the very beginning of early Noachian history, right?
I was thinking middle Noachian, say, for example,
okay.
In the vicinity of one of the three.
Yes, so probably, yes. I mean, when OP-type clays form, they are already draping the dichotomy and also the outlet valley of the Mars valleys. So I guess they happened during early Noachian to middle Noachian time. They are dated in Oxyaplanum to be about 4.0 billion years old. Yes.
Keep it in mind.
Anos Kladaris from Purdue University. Really great talk, by the way.
Thanks.
And I think the identification of that cratered paleosurface is a really important breakthrough, I think, for linking these areas. And my question actually was about your OP-type clays. Some really nice spectral plots, and one of the differences you showed is that your OP type clays, which you're interpreting as like more magnesium bearing,
Yes.
had a really strong ferrous iron slope. I was wondering, how did you interpret the cause of that? Could that be like primary mineralogy, like something like olivine, or some kind of ferrous alteration phase within the magnesium?
Yes, so I think the difference between the two types of clays is mostly during alteration conditions, maybe more than the protolith. And I guess, I mean, it's just a thought, but they must have formed during more reducing conditions, which proved this ferrous slope to happen, because the non-tronite unit really doesn't have this strong ferrous slope. Maybe they are also intermixed with olivine, so in oxyaplanum there's also an olivine-rich unit, so it could also enhance this, maybe this signal of ferrous slope. Yes.
Nice, thank you.
Thanks.
Samantha Baker, Caltech, really great talk. I'm curious, in your regional map where you show the relative strengths of the Marthalis to oxyplanet
Yes.
types, there seemed to be, maybe I'm mistaken, but there seemed to be kind of an area, there was an, yes, perfect. In Marthalis, there's that really
Yes.
strong red concentrated
Here,
area. Where
okay.
There's, strong OP exposure. Is that just an area of enhanced erosion where we've removed the, or like how do you interpret that?
So, I'm sorry. Exactly in this specific place, so I had to remove many slides, but here actually there's a big crater. I think it's about 10-kilometer diameter. No, yes, 10-kilometer diameter. So maybe it's ejectas from this crater, and actually with the chrism mapping of this cube, we can see the crater wall with the basal unit of the crater wall being full red, and then upper crater wall unit being blue. So I know crater walls can be hard to interpret. Maybe there are some inverse stratigraphy with the impact, but I mean, it could be that indeed we ejected many clays from this OP-type basal unit, which is present in Mars valleys.
Okay, last question.
Bethany Ellman, University of Colorado. So thank you for the excellent talk and the analysis. I wanted to come back to some of your conclusions at the very end about environment. And in particular, yesterday there was, some back and forth about whether there was an ocean or not.
Yes.
In my mind, your study area is one of the most important areas that I think demonstrates the continuity of alteration from plateau to within the putative ocean basin, and basically is showing that there's actually relatively little difference. I wanted to understand a little bit how you see and analyze the question, because I found it curious that you ruled out lacustrine but did not seem to rule out ocean. And so I was wondering if you could comment, just based on your own analysis of this, how likely an ocean ever was in this area, and if it was there, what kind of deposits would it be, or do you think it was not, that there was not a lake, or that this was not a subaqueous setting? I'd be curious your thoughts.
So I don't completely rule out the ocean hypothesis, but I think it's still challenging, and with this study we pose some strong constraints. So if we look at this plot, so what's important here is that if there was an ocean forming, for example, the OP-type clays, so then it would have to be followed by an ocean retreat, because as we interpret the top of the OP-type unit to be this paleocratered surface, it can only form under subaerial conditions. So it would have to retreat at least to where we don't see it, which is the delta catchment elevation here. And after that, if there's an MV-type deposition, so it happens at this elevation in Oxia, but we also find these deposits to be at lower elevation in the top of Mars Valleys plateaus, so here. And if we think that maybe this is contemporaneous to the existence of an ocean, then the level of the ocean should be the same in the planet. So of course, topographic change happened with after the true polar wonder, but here we would talk about 400 meters. So we would have to have the base of the MV-type deposits at the same level as the base of MV-type deposits here. So it's 400 meters of elevation vertical shift over only 400 kilometers. So maybe it's possible, we should investigate, but as a comparison, for example, the Hypanis Delta, it's only 200 meters above the Oxia Delta elevation. So if it's contemporaneous to this same ocean, and it's way further away, it's hard to believe Marsalis would be 400 kilometers below. I don't know if it's that clear, but...
I think it says
okay.
the ocean is less likely as a result. Otherwise, you have to
Exactly,
have Mars
yeah.
doing this. Yeah.
Okay, thank you. So let's thank Ines again. We have to move on. So our next speaker is Brian Jorgen, and we are talking about more and more of clays. So the talk is going to be on the compositional clay stratigraphies as indicators of paleoclimates on Mars.
Great, thank you. Wonderful. Well, bonjour. It's lovely to be here. I'm full of pastries and coffee and very happy to talk this morning. Okay, so today I'll be talking about compositional clay compositional stratigraphies, which is the technical term we're using to non-interpretively describe these kinds of deposits, which we've heard about this morning already. But these are, I'll call for short, clay stratigraphies. These are outcrops that have been discovered across the southern highlands of Mars that show aluminum clays overlying iron magnesium clays, as shown in this nice figure from Thanos' paper out earlier this year, shown in 3D, where the blue here is showing materials with a 2.2 micron band indicating aluminum or silicon bonded with OH. And then below that in red, the 2.29 or 2.3 micron band showing iron magnesium bonded with OH. And so this stratigraphy we see where we have the blue overlying the red indicating this difference in clay composition has been observed globally at more than 200 sites by several groups that have been studying this for many years now. And what's really fascinating about this relationship is that this aluminous material overlying iron magnesium material that changed from 2+ cations or less than 2+ cations to 2+ cations below suggests you had significant leaching to form this relationship. And based on that, on Earth, we see very similar kinds of deposits that are formed by rain leaching water through the ground to transport those 2+ and below cations down to leave behind that aluminous material above. So, but these are really interesting because these deposits are potentially, in this hypothesis, directly interacting with the atmosphere. And so they represent a place for us to potentially look for records of what the climate and atmosphere were doing at this very important period of time during the Noachian into the early Hesperian. So we have many outstanding questions. We've been looking at this in a collaboration with, from my group and Tim Gouge at UT Austin and Bill Farrand at Space Science Institute. We've been looking at questions like, do these clay stratigraphies consistently show evidence of forming as deep leaching profiles? Just a very basic question. Is that consistent across the planet? Is there a clear link between the clay stratigraphies and ancient climate? What types of climates would we expect to form these clay stratigraphies? And then what atmospheric or environmental redox conditions are recorded in clay stratigraphies? So you can see a whole range of questions. And so here today I'll report on 2 papers that were published earlier this year from our collaboration and then also some ongoing work that will be of interest to this group. So first off, from Thanos' paper earlier this year in geology, he took a very, sorry, this is really hard to see from this angle. He took a very close look at the topography of the clay stratigraphies, trying to understand basically what is the relationship between the aluminum unit and the iron magnesium unit globally at all the places we have overlapping CRISM and high-rise DTMs. So very carefully tracing the relationship, the boundary between those 2 materials, and then looking at the CRISM detections above and below that boundary as it was traced in high-rise. And found first off, just very nicely, that about 90% of the iron and magnesium clay pixels lie beneath the boundary horizon, suggesting that there isn't really much intermixing. It really is, in the vast majority of locations, strongly bifurcated into those 2 different materials. So that this relationship is very consistent. And secondly, that these clay stratigraphies clearly drape topography shown very nicely, as shown by previous authors, but here shown quantitatively, that the aluminum unit very clearly drapes Marth Vallis over more than 1 kilometer of elevation. So this strongly supports a top-down leaching model for glacier stratigraphies, so we're confirming what previous authors have suggested. Okay, so next question. This is from a paper by Rihanna Moore out of Tim Gouge's group at UT Austin. We were looking at the global distribution of glacier stratigraphies and what can that tell us, their distribution, what can that tell us about what controlled where and when they formed? And so these are weathering profiles. On Earth, these things tend to form in tectonically stable regions that aren't experiencing much uplift and have fairly low erosion rates. And so that was our hypothesis going in, is that we should find these things in areas with low erosion rates and potentially in areas that have locally more humid climates, potentially. And so in Nature Astronomy, Rihanna was able to show that, Rihanna did a really nice study comparing the distribution of the 150 glacier stratigraphies from the Carter et al. Papers to a variety of other data sets to try to understand their distribution. So including randomly sampled points on other Noachian and early Hesperian terrains, other clay mineral detections, the valley network dissection level, then also paleo lakes and basins. And her work was able to show that there is, first off, the distribution latitudinally of the glacier stratigraphies is anomalous compared to both ancient terrains as well as other clay detections. And so you can see in the plots at right, on top, the black bars correspond to the glacier stratigraphies, whereas the purple are the ancient terrains, the green is the valley networks, and on the bottom, the blue and red correspond to the other clay detections. And so you can see that the glacier stratigraphies do have this very strong latitudinal concentration between about 20 and 30 degree north and south. About more than 60% of them occur in that range. And so that's very different from, again, these other ancient characteristics of the Noachian, which is interesting because that concentration coincides with the tropical to subtropical latitude band. We've seen a few nice climate maps, yesterday showing where you might expect enhanced precipitation, and that's one of those locations, so that's really interesting. And that's consistent with some ideas about where you might expect to find more water. So one thing that's interesting too is when we look at the relationship between glacier stratigraphies and valley networks, we find that glacier stratigraphies tend to occur, compared to other ancient terrains, they tend to occur in areas with lower elevation, less valley network dissection, as well as shorter, more discontinuous valley networks, whereas those two properties we were treating as proxy for erosion rates. If you have more dissection, you have more valleys, you have more local runoff and erosion. They also tend to occur closer to large basins and paleo lakes, and so that could be a proxy for local climate if those were bodies of water at one time. And so that's really interesting because it's suggesting that we have glacier stratigraphies forming where we have lower erosion rates. Basically, in the cartoon at bottom right, you can see we have this sort of upland terrain where there's lots of dissection and lots of erosion. You get down into the more flatlands, that's where you tend to get, we would expect to find chemical weathering outpacing physical weathering because the erosion rate's fairly low. And that's because we have infiltration beating out runoff in that case. So that's looking at the kind of global climate connection. And now we can also look at the properties of the glacier stratigraphies themselves. So the other key result from Thanos' paper in geology this year was looking at the thickness, trying to measure the true stratigraphic thickness of these glacier stratigraphies, both the aluminum unit and the iron magnesium unit, looking at the actual dip and trying to calculate true stratigraphic thickness using Tim Gouge's techniques for this. And so what Thanos found in these locations where we have this overlapping high-rise and chrism data was that we see thicknesses, total thicknesses of the whole package ranging between 6 to over 200 meters globally. The mean is about 59 meters. If you look at the aluminum unit, which is the part that we're sure that part is part of the weathering profile itself and not, say, some underlying material that was pre-existing, the thickness of that itself ranges between 4 and 78 meters globally with a mean of 26 meters, with 20% of those exceeding 50 meters. This is extremely, extremely thick, right? We do see weathering profiles this thick on Earth. The thickest ones we know of are about like 160 or 180 meters. So it's not out of the realm of possibility, but it's definitely on the deeper side. What's really interesting is that in terrestrial literature, it's been shown that the maximum thickness you can achieve of a weathering profile is very strongly correlated with precipitation rates, right? Mean annual precipitation. And the way to think about that is to extend the depth of your weathering profile, you have to have enough water to percolate and infiltrate down into the subsurface, saturate it, and then fill up that zone, right? And then go down and start altering at the base. And so if you're talking about tens of meter deep material, regolith or rock, that's a lot of water that you have to have instantaneously present in the system. And so that means to get really deep profiles, you have to have a lot of water kind of in the system at any given time. And so that's why there's a strong correlation with precipitation rates. Now, we're very hesitant to directly apply any Earth kind of quantitative measure to Mars, but it is useful as a frame of reference. And so there is a nice rainfall to thickness relationship that has been determined from Hawaiian laterites. And that's nice because it is a compositional and kind of material analog for Mars, but we have all kinds of concerns about does the process operate the same way, for example, in the absence of life, all these other questions. How does temperature affect it? We're not sure. But just as a reference point, for the thicknesses we're talking about, just the average thicknesses, either for the aluminum unit by itself or for the full profile, that would correspond to something like a minimum mean annual precipitation of between 800 to 1,500 millimeters per year for these kind of average clay stratigraphies. For those who don't think in these numbers, that's ranging from like where I live in the semi-arid part of Indiana down to like maybe south of Atlanta in the US. So it's kind of semi-arid to somewhat humid climates. Okay, so that's kind of getting at the general climate connection. Now I just want to spend a few minutes briefly talking about some ongoing work we're doing looking at the redox state of the clay stratigraphies, which is really interesting. So some really excellent previous work by Liu et al. In 2021 showed that the clay stratigraphies are, intriguingly, this very distinct gray to blue in color, at least in their upper horizons where the kaolinite and other aluminum clays are located, suggesting that these are largely reduced and that they probably formed under a reducing atmosphere. But there is some evidence that there's more local complexity in the redox state. We have observations of iron and sulfur-bearing redox-sensitive minerals like acid sulfates, iron oxide, things like that. So we're very interested in understanding what this is telling us about the environment or perhaps the atmosphere that they formed under. Today we're going to focus on just the hematite detections as an indicator of oxidation state. And so just as an example, so here's one of our favorite scenes of clay stratigraphies from the southern edge of the actual Marth Vallis channel. On the left showing the approximate natural color where the light stuff is the aluminum unit, and going down slope into Marth Vallis. In the middle, we can see that the clay mineral map, where blue is the aluminum, pink is the iron magnesium. And then on the right, we can see a map where we're trying to highlight things that have absorptions around 900 nanometers, which includes hematite. And so in this stretch, hematite corresponds to red colors. And there's also potentially some other ferric minerals in the yellows. Those correspond, you can see very clearly, to that upper aluminum unit, which is very interesting. Here's an actual spectrum just to show that this is in fact there. So this is just an average of, in this scene, all the pixels that have strong 860 nanometer bands compared to a standard USGS red hematite spectrum. And you can see that it has the hematite 860 nanometer band, as well as a strong hydration and aluminum SiOH band consistent with the upper aluminum unit. We see this basically everywhere at Marth Vallis, but also globally in many locations. Here's another example from Mara Crater, another classic location. Showing again on the right, you can see that red to kind of yellow, very patchy behavior within that upper aluminum unit, suggesting it's kind of here and there within the unit. Okay, so how did this form? There's a couple different mechanisms which are of interest depending which way it goes. So first off, this could be a very local process. This could be that hematite formed in very local redox gradients really caused by surface environmental conditions. This could be, because we see some relationships with other kind of patchy redox sensitive minerals like acid sulfates, potentially ferrous clays and things, that this could support that kind of mechanism. On Earth, we see these kinds of mottled soils all the time. It's very common, especially when you have groundwater fluctuations, water table going up and down, kind of changing the oxidation state. It's a lot easier to do that when you have an oxidizing atmosphere and that exposure causes oxidation. But other things can cause this too. On Earth, biology notably can cause this kind of oxidation. On Mars, how would you cause oxidation? If you don't have an oxidizing, you could have an oxidizing atmosphere, that's an option. If you don't have an oxidizing atmosphere, you have to rely on other things like, say, UV radiation. We've heard about the Hurwitz model for UV radiation causing photolysis and things in shallow bodies of water. That could be an option here. We have shallow little bodies of water and kind of a saturated wetland type environment causing localized oxidation. So in that case, you could have this kind of broadly reducing atmosphere with these localized, what we call kind of oxygen oases. And that's potentially important because on the early Earth, these types of locations, or these like localized oxidizing areas, are thought to have been really important in the development evolution of life. Okay, but there is another option I think we should think about, and we're trying to poke at this more in our data, which is that on the right here, I'm actually showing one type of laterite that exists on the Earth. Laterite is the classic highly oxidized, deep leaching profile that occurs on the Earth. And typically we think of these as very red and oxidized, but here you can see it also has this very white bleached pallid zone, and that corresponds to strong kaolite detections. And basically this forms under an oxidizing leaching condition, but where you have fluctuating groundwaters causing bleaching off and on in, like, say, a seasonal climate. And this is interesting because this indicates, on Earth, oxidative weathering under an oxidized atmosphere, but unless you can see that upper really oxidized horizon, it's very easy to erroneously interpret this as indicating a reducing atmosphere. And this was actually true for a long time on Earth until these kinds of units, the outcrops, were reevaluated and shown to be actually consistent with great oxidation event kind of processes. So this is interesting. It's, could this be analogous to some of the modeling and hematite detections we see on Mars? TBD. Just show you the distribution of hematite-bearing things. They are, in fact, all over the place with some latitudinal distribution. And then to end it off, I wanted to just summarize our results for the climate modelers, which is a big chunk of the audience. So you all can start thinking about how some of these observations might impact some of your models. So we see this strong latitudinal control on clay stratigraphies, as well as some relationship with large basins. Based on Earth analogs, we think these require significant precipitation rates, mean annual precipitation rates to form over potentially some extended period of time. Because these happen over we see a range of ages of these things, that suggests it wasn't just one event, it was many events over a long period of time. And also, just based on our geological investigations, these things do really require rain. We cannot, as far as I know, cannot form them with melt, snow melt, ice runoff, things like that. You have to have rain infiltrating into the crust. And then we're currently working on kind of oxidation state and what that's telling us. But that's it, and I'll take any questions.
Thank you. We have time for one or two quick questions.
Hey, Bryony, Ali Rutledge, NAU. Great talk. Thanks so much. I had a quick question about that really cool crater, the rim you showed.
One?
Yeah, have you considered at all that some of that might be related to crater rim hydrothermal systems?
So it could be, right? But so here this is the same relationship we see all over the plateau nearby. It's this very consistent kind of Marth-Vallis alumina over iron magnesium relationship that we see draping Marth and kind of all over there. So here I would say probably not.
I was wondering more about the hematite.
Oh, the hematite.
Is that also consistent?
Yeah, that's an interesting question. I would say that not necessarily, well, yeah, so here I guess I would say because it's not unique to this crater. Again, we see it kind of throughout this whole, even going back to this one, right? Throughout this whole region, unrelated to cratering, but it's something to think about. How could that be modifying these for sure? Yeah.
Very excellent summary there. A little caution on the 20 to 30 north concentrations.
Yeah.
I would encourage you to put the late Amazonian latitude-dependent mantle on there because that really provides a mask, and if you can do that and show that it's still 20 to 30 north concentrations, that's fine, but I think that's a warning. I think it may be dictated by latitude-dependent mantle.
Well, yeah, and I would say that's where the comparison, which I really appreciate that Rihanna did, the comparison to the other clay detections, because that's a much broader data set of just chrism detections of alteration, and we do not see the same trend there, even though that's just as dependent on exposure and mantling and all that stuff. So.
Right, thank you. Next speaker, I will try to pronounce it well. It's Athanasios Didaras, so from Purdue, that we talk more about clays and the signatures of weathering on the ancient Mars from a global spectral database of Martian CCS.
Good morning, everyone. My name is Thanos Klidaris, and I'm working with Bryony, and I really appreciate Bryony's talk and also all the other talks we've heard already for setting the context for what I'm going to talk about. And so I'm really just building off of what Bryony has been talking about. We're working on building this global spectral database of Martian compositional clay stratigraphies, and I'm really going to talk specifically about the aluminum unit in this talk here, which we haven't heard much about yet. I can skip some of these introduction slides since hopefully you already have heard about what these might be. And here's a generalized stratigraphy of a compositional clay stratigraphy. It's found sort of all over Mars. Here's a really generalized version, but it's this upper aluminum unit that's the focus of my talk. And that's because these aluminum phases record intense aqueous alteration. There's plenty of outstanding questions. For example, are these really one single deep weathering profile? Or maybe in places, they might actually be weathering of different packages of material and placed on top of each other, maybe under varying environmental conditions. And then also like what the protolith is, how was the protolith in place? Maybe pyroclastic or sedimentary processes. And thank you, Bryony, for introducing this paper that came out in geology where I measured the thickness in a lot of detail. But here I'm going to talk lots more about the spectra that we see. So since these are inferred to have formed through weathering, like subaerial weathering at the surface of Mars, they're a record of surface, near-surface conditions during the Noachian. And this makes them incredibly valuable to a lot of the outstanding questions we've talked about like in this conference this week. For example, what was the nature of the Noachian atmosphere? When, if ever, were warm and wet conditions reached? And what was the redox state and pH of surface, near-surface fluids? And of course, that all feeds into questions about habitability too as well. And what we're doing is we're building a spectral database of compositional clay stratigraphies to help address some of those questions. And so for all 125 CRISM TRDR images in this paper, Carter et al. 2015, and here's a map of their detections for reference, our automated pipeline performs a bunch of steps, including continuum removed band center mapping, extracting spectra from high band depth ROIs, and extracting some of the Viviano et al. Refined spectral summary parameters. And for more on that, you can see my LPSC oral presentation, which I gave earlier this year. But I'm really going to be talking about spectra in this talk from these high band depth ROIs. And I'm going to show you how I produce them now. So let's take any CRISM image, and this is a really nice one in Marth Vallis. I believe this might have been the area which was proposed as a possible landing site for MSL and M2020. And here's the steps that my code performs. So we calculate the continuum removed band centers across this image, and then we mask out low band depth pixels because there's lots of things like regolith and perhaps later volcanic units which lack a clay signature, and in my case, we're not really caring about those. We're then going to classify the alteration minerals by their band center, and the product of that is this lovely colorful map. And here I've subdivided things into 6 different band center groups corresponding to aluminum rich, aluminum and silica rich, intermediate region, iron rich, iron and magnesium rich, and magnesium rich alteration minerals respectively. So we can do one step further, and this is the progress that I've made in recent weeks and months since my LPSC presentation. We can take all of those, for each of those colors, right? We're going to isolate the highest band depth pixels because we want to get a region of interest and get a nice quality spectrum out of it. So we isolate the highest band depth pixels, and then I have code that will identify contiguous clusters because a region of interest should be a kind of a reasonable shape that a human would draw rather than kind of scattered pixels all over the place. And I basically loop through them to find the cluster that has the largest size and that meets these 2 valid criteria, that needs to be bigger than 15 pixels across, and it needs to have certain aspect ratio shape for it. And this is the end product of that. So now, taking that top image, we've identified, in this case, 4 large contiguous regions of interest. And using this, we can extract spectra. So let's just look at this. This is the iron-rich band center group, which corresponds to clays like nontronite. And when we look at the spectra, voila, we have a lovely, strong absorption clay signature, and the band center at 2.29 microns is exactly consistent with nontronite. And this actually aligns really well with what was said earlier this morning where people were talking about the specifically kind of non-trinite flavor of clay at Marth Vallis specifically. So it's really nice to see that all lining up between our talks. So now I'm going to talk about the aluminum unit and the diversity that we see across it. This is going to be really important for trying to tease out what the environmental signatures clay stratigraphies are recording are. And so globally, what I did is I literally manually reviewed all like hundreds of aluminum unit spectra. And what I found is that the most common signature, spectral signature in the aluminum unit is basically this asymmetric band, where we have a band center at about 2.205 microns. Let me get the laser pointer out. So at about this point, which is a match for the band center of kaolinite. And it's also asymmetric, so it does share some shape properties. However, what we don't see is the doublet. So at 2.165, kaolinite clay has this doublet, and we're not seeing it here. So this is vaguely suggestive of kaolin clays, but lacking that doublet. Why might that be? It could be that CRISM's spectral resolution isn't sufficient to capture that. However, on the next slide, you'll see I don't think that's the case. It might be poor crystallinity. I think this is possible as well. Maybe that means the features aren't displaying as clearly as in these lovely, nice lab spectra. But what I actually think is going on is mixing, right? Remember, these are not powdered, pure samples. These are CRISM spectra of real rocks on Mars. Real rocks are mixtures, and I think what's likely going on to get a shape like this would be a mixture between kaolinite and then some other aluminum and silica-bearing alteration phases, perhaps montmorillonite or allophane, and that might, in my imagining, kind of make a sort of broad asymmetric shape like this. However, despite saying that, we do actually find clear kaolinite and halloysite-like spectra. Halloysite is just a polymorph of kaolinite. So here's a really nice example. We see it in 3 places. So Marth Vallis, Northeast Syrtis, and Terra Cimmeria, Terra Serenum. We have strong spectral evidence for kaolin clays. So here, again, are the 2 doublets, and now we're actually resolving that doublet at 2.165. And this is really exciting, and I'll get onto the environmental implications for that in my next slide. But I just wanted to point out, let's look at this bottom spectrum here from Terra Cimmeria, Terra Serenum, which is a really clean kaolinite spectrum. Actually, when you look at the region of interest this was taken from, it's not just a small ROI, it's actually 2,800 pixels. And that suggests that at least at this locality, we seem to have a really pure concentration of this one aluminum alteration mineral. Used for paleoclimate reconstruction, so super relevant to the topic of this conference. And the reason why it's used in paleoclimate reconstruction is because it's really common in subtropical to tropical soils on Earth. And here's a figure from a book which is showing how soils vary with latitude on Earth from the poles to the equator. And what you can see is that kaolinite-bearing minerals really are specifically concentrated in the subtropics and tropics of Earth, so places like South America and Central Africa. And obviously that would be really profound if we're really considering those places like Central Africa as an analog for Noachian Mars. We do see other signatures, though. So one of them is that we see just symmetric bands, and sometimes these have band centers that are consistent with aluminum smectites like montmorillonite. Badolite is another aluminum smectite, but its band center is about 2.18 microns, and we're not really seeing that yet, but it could be because those exposures are kind of small, and just by chance, my region of interest algorithm is not capturing that. So something to look into. And then occasionally, and often at Northeast Syrtis, actually, in particular, we see further bands at about 2.26 microns, consistent with jarosite. So here's a lab spectra of jarosite. And if you look at this bottom spectrum, it's actually a really good fit. Now, this has been seen before, and sometimes it's actually in the same spectrum, we have aluminum phyllosilicate and the jarosite, and these have been termed doublet spectra, and they've been seen in Marth Vallis before, and potentially interpreted as forming in like saline, acidic, evaporitic ponds. And actually, the following talk after me is going to discuss jarosite in more detail, so that's nice. And then finally, we do see some other symmetric bands with band centers about 2.19 microns, and these might be consistent with poorly crystalline or amorphous phases like allophane and amogolite, which actually has very different environmental implications where we detect this, but is consistent with previous detections by Janice Bishop and Liz Rampe in Marth Vallis. Here's a false color composite I've put together, looking at the different band depths across the aluminum silica absorption feature, and we can visualize the aluminum diversity. So in this case, the orangey, bright yellowy stuff corresponds to that doublet between asymmetric aluminum phyllosilicate and jarosite. Then there's this big red patch at the top, and this actually is the ovoid-shaped jarosite deposit that was discovered by Farrand et al. 2009 in Marthalis. But you'll notice there's also some lighter tone bluish pixels, and this color composite suggests they might have shorter band centers, perhaps consistent with things like allophane or perhaps betadite, but I need to interrogate the spectra to confirm that's the case in this example. So in summary, here's kind of like the 5 aluminum unit spectral classes that I'm seeing: the asymmetric one, kaolinite and halloysite-like, possible montmorillonite-like, the jarosite-like, and possible allophane or amogolite-like. So something that's interesting when we basically try and plot this on a map is that there's a lot of diversity. So we see these different phases both varying between different regions, but also just within individual regions. So there's a lot of complexity here that will be interesting to try and tease out. And in this map, the sort of dashed lines indicate sort of moderate uncertainty, whereas the solid colors are more certain detections. And let's try and piece together what this might be suggesting about Noachian climate, because it is quite puzzling. So on one hand, this widespread evidence for kaolinite halloysite, that's really indicative of intense chemical weathering associated with leaching, potentially under a warm and wet climate, as been proposed before. Where we see things like montmorillonite, we're talking about more like an intermediate degree of chemical weathering. Something that's interesting is that montmorillonite is a common weathering product of volcanic ash, which has been proposed as a possible protolith in some cases. Where we see the jarosite, sometimes sort of mixed with the aluminum unit, but sometimes just dominating the aluminum units, that suggests acidic conditions in places, maybe evaporitic ponds. But I'll point out that where in these instances, it suggests we have low pH surface fluids, and that low pH might permit the really intense chemical weathering we're seeing with the kaolinite and stuff, but under like more moderate conditions. So maybe not super warm, but maybe just like temperate or cool climates, perhaps under briefer climate excursions, because the acidity increases the rate of clay formation. And then at the bottom, we're seeing these possible exposures of really incipient clay minerals, like amorphous, polycrystalline phases, and that suggests there are horizons in these clay stratigraphies where actually there's only incipient, only beginning chemical weathering, maybe under cool or very brief water-limited conditions. So, you know, all these different assemblages are all suggesting quite divergent environments. And what I think is really going on here is that there's a lot more complexity. I don't think there's a single kind of Noachian climate or a single Noachian clay stratigraphy forming climate, but rather there's some really complex story involving varying environmental conditions, both spatially and then with time stratigraphically. There's a dimension there too. And so in summary, we are developing a global spectral database of these Martian compositional clay stratigraphies, and we've already observed a lot of variable mineralogy in the aluminum unit, including kaolin, acid sulfate, aluminum smectite, and maybe some amorphous or polycrystalline phases altogether. And this really complex, both intra and inter-regional variation is suggesting a complex story at these sites, and likely a spatially or temporally, probably both, varying Noachian climate. Thank you for listening to my talk.
Thank you. We do have time for a few questions.
Thanks for the great talk. So I had a question concerning your method. Do you use any specific denoising method, or do you just manage to get a clean CRISM signal doing arrays of clusters?
Yeah, so I'm actually just using the TRDR PDS pipeline CRISM products. So they've had the sort of cat NV tools applied, but no, I'm not doing any like column-specific ratioing to suppress the noise. I'm just sort of learning to suffer through the noise. And I'm not ratioing the spectra either. So these are just kind of pristine, unratioed spectra. I do actually have the code to implement ratioing, and I'm curious to see whether that would really accentuate some of these absorption features. But just for now, I've just presented all the spectra the same way, which is like sort of pure and unmodified as possible.
I do have a question. On Earth, when we are looking at kaolinite weathering profiles, sometimes kaolinite can have iron in its structure, so by substituting from the aluminum, and we do see that in the doublet, because we have a tiny absorption at maybe, for example, in the 2.2 absorption at 2.25 or something like this. Do you see that in your spectra on Mars?
Well, that's really interesting. I wasn't aware that iron substitution might cause like an absorption, but that kind of makes sense. We do have lots of spectra where we're seeing this kind of asymmetric shape, potentially kaolinite influence, where we have an absorption about 2.26. But in this case, I'm interpreting it as jarosite in line with other studies. But yeah, that's something to explore, that maybe some iron contamination might cause a spectral shape there. And then, of course, something that has often been seen with the aluminum unit, especially in Mare Vallis, is a kind of ferrous slope out in the kind of near-infrared, shortwave infrared. And that is something we're seeing as well. And something I'm going to follow up with is mapping out the distribution of that ferrous phase and trying to figure out what it might be.
All right, thanks.
Thanks.
Okay, let's thank our speaker again. So last talk before the coffee break will be given by Samantha Baker about aluminum phyllosilicate and jarosite alunite formation from probable volcanic ash deposits across Mars.
All right, hi everyone. So I'm going to be continuing the conversation about these clay compositional stratigraphies, but possibly coming to a slightly different conclusion that some of these aluminum phyllosilicates, as well as jarosite and alunite, formed from possible volcanic ash deposits. And you have already seen this figure today, so I won't spend too much time going over it, but just as a reminder, we see aluminum phyllosilicates across Mars, primarily in these areas where they're seen overlying iron magnesium phyllosilicates in what may be these possible weathering sequences. And as we have heard, there are a number of alteration products that are associated with these, but for the purposes of my project, I'm primarily focusing on sulfates in the jarosite to alunite solid solution, and these are sulfates that form under highly acidic conditions. And we can see that they have been found associated with aluminum phyllosilicate in most of these regions. And there are two primary theories at the moment for aluminum phyllosilicate formation. The first is that they formed as part of these top-down weathering sequences. So if you start with the basalt, they weather first to iron magnesium phyllosilicates, and then through more intense alteration to aluminum phyllosilicates. You can also get similar mineralogy if you start with two different protoliths. So a basalt that's topped by something like an aluminum or silicon-rich capping unit, and that can weather directly to aluminum phyllosilicate phases, though in this case you would get unconformities between the minerals. And detailed analysis of the aluminum phyllosilicates in Terra Sirenum has found some evidence for both of these methods. Aluminum phyllosilicate units within Eridanea Basin, which is within Terra Sirenum, likely formed as part of a weathering sequence. However, elsewhere in the region, thick aluminum phyllosilicate units likely formed from a volcanic ash deposit. And this is indicated by both fine, meter-scale layers within the kaolinite units, as well as a distinct increase in thickness as you get closer to the proposed volcanic source of Arsia Mons. In this region, aluminum phyllosilicate is associated with alunite, with sulfur likely sourced from either volcanic or magmatic origins. And so inspired by this, because this analysis found this potential volcaniclastic origin for some of the aluminum phyllosilicates, we're reanalyzing the formation of these units globally, because these conflicting theories remain about their formation. Also, in some cases, particularly in Nili Fossae, new orbital images have been acquired since previous comprehensive analysis. We also apply the same methods in all locations to be able to examine and interpret these units with a uniform perspective. And I'll note that differentiating between these end-member processes has significant implications for things like calculations of water abundance and duration, as well as Mars's geologic evolution more broadly, which I'll get into. So here you can see, probably looks familiar, some CRISM examples of some of the key mineral phases for this question. And differentiating these phases in the CRISM data is challenging because of noise, but also because there's a clustering of a lot of the diagnostic absorptions, like right around 2.2 microns. So we developed and implemented a method of using Gaussian fitting to key absorption features, some of which I've identified here, to identify minerals based on the depth of the fit curves, as well as their width and center position. And we also fit 2 Gaussian curves to be able to consistently identify jarosite even when it's mixed with aluminum phyllosilicate. All right, diving right into our results for Nili Fossae, which has been the focus so far. Here you can see the Nili Fossae region with the locations of all of the key minerals that we detect. And consistent with prior literature, aluminum phyllosilicate is consistently stratigraphically above iron magnesium phyllosilicate. We also find that this mineral is dominantly kaolinite in composition, and it's associated sparsely with jarosite and also with nearby iron oxide. We find that kaolinite is preferentially associated with sedimentary basins, and in this case we're referring to impact craters and eroded topographic lows on the 50-kilometer scale. Here you can see the distribution of all of our kaolinite detections in the region, and those that are in white are in basins at this scale, which is 2/3 of them. This was corroborated with CRISM's multispectral mapping imagery, which shows that all large kaolinite deposits, at least those that are detectable in that imagery, are located in topographic lows at this 50-kilometer scale. Examining the high-resolution imagery reveals some key stratigraphic relationships, and I'll show evidence for all of this, but I'm just going to start by stating them. We see that kaolinite typically has a different texture than the iron magnesium phyllosilicate, that we see that jarosite is closely associated with kaolinite and not with not with iron magnesium phyllosilicate, and that iron oxide is uncommon, and it's stratigraphically below kaolinite where it occurs and not mixed with it, which is unexpected for a weathering sequence. I'm going to focus on 2 sites to show some evidence that I've circled here. They're both in impact craters just to the west of the fossae. So starting with site 1, that northern site, here you can see our mineral maps with kaolinite in blue, jarosite in red, and iron magnesium phyllosilicate in green. And you can see that the kaolinite and jarosite are in these like fine meter scale layers, and the iron magnesium phyllosilicate is not. It's in this layer or unlayered knobby unit, and there's unconformities between an unconformable contact between the minerals. And this is one of our areas where we have our best clay exposures in the region. Nearby in that same image, we have a kind of shallow pit that's been filled in with, again, kaolinite and jarosite mixed in these meters scale layers, which is in stark contrast to the surrounding iron magnesium phyllosilicate that forms this unlayered knobby unit. Moving on to the second key location, we've mostly focused on this like multi-level plateau that's been exposed by erosion. And here we can see kaolinite that's been exposed around the edges of the plateau. And if we zoom in, we can see kind of eroding out of these cliff faces, showing meter-scale polygonal fractures that are distinct to the underlying terrain. Also, you probably noticed a lot of purple in these mineral maps. That's that mixture of kaolinite and jarosite. And we can see that they're strongly associated. In that northern example site, jarosite is intimately mixed with the kaolinite, and it's not mixed with the iron magnesium phyllosilicate. Also, we don't see any iron oxides detected in this region. In our plateau area, we again see jarosite associated with kaolinite, and if we zoom in, we can see this like dark patch, like a discrete jarosite patch that is in contact with and mixed with the kaolinite. We do see iron oxides present in this area. They're located stratigraphically between the kaolinite and the iron magnesium phyllosilicate. And if we zoom in on the iron oxides, we can see that they're of a distinct texture to the kaolinite. They lack those meter scale fractures. All right, so what can we conclude about Nili Fossae from this? Well, I'll walk through it towards our conclusion, but we find that kaolinite most likely formed from aluminum or silicon-rich volcanic ash in this region. We observe that kaolinite is associated with sedimentary basins. It typically differs in texture from the iron magnesium phyllosilicate, and where contacts are exposed, they're unconformable. And this suggests that kaolinite formed from some kind of transported sedimentary material that was distinct from the iron magnesium phyllosilicate protolith. This kaolite protolith weathered into aluminum-bearing phases, with the exception of jarosite, which I'll get to, lacking iron oxide, which could suggest that the kaolite protolith is of a distinctly aluminous or silicious composition. Also, jarosite is associated with kaolinite, not the iron magnesium phyllosilicate. And this is unexpected because jarosite is an iron sulfate. To form, it needs iron, sulfur, as well as oxidizing conditions. And so if you had sulfur-rich fluid moving through the system, you would expect it to form alongside the iron magnesium phyllosilicate. We propose that jarosite may have formed from fluid that was enriched in iron that was leached from the surrounding iron magnesium phyllosilicate, but the requisite sulfur was sourced locally from the kaolinite protolith. And if it was an ash, we would expect it to be bearing sulfur-rich phases. So that could explain why we see the jarosite associated with the kaolinite. And then these iron-rich fluids could have produced iron oxides where there wasn't enough sulfur to form jarosite. So looking back at the global scale, previous work has found that at least some aluminum phyllosilicate formation in Terra Sirenum is likely from volcanic ash. And we find in Nili Fosse that aluminum phyllosilicate also likely formed from volcanic ash. The global analysis is ongoing. Hopefully in a future conference soon, I'll be able to present more on it. But just as a quick sneak peek, in Marthalis, we found new detections of jarosite mixed with aluminum phyllosilicate. And in Libya Montes as well, I think the first detection of jarosite in the region also with aluminum phyllosilicate. So just to summarize these results and talk about some of the implications, we're finding that aluminum phyllosilicate across Mars likely formed through different methods, and at least some of it was from a separate protolith that was deposited unconformably over the iron magnesium phyllosilicate protolith, probably an aluminum and silicon-rich volcanic ash or other fine-grained pyroclastic deposit. This appears to be the case in Nili Fosse and parts of Terra Sirenum, possibly Marthalis, previous work has suggested it, and other regions as well as Marthalis require further investigation. Jarosite appears to form contemporaneously with or shortly after aluminum phyllosilicate in these locally produced acidic conditions. And this has significant implications for Mars's aqueous as well as its volcanic histories. Starting with the aqueous, an ash protolith, rather than formation through a weathering sequence, indicates that a scenario with more limited water is possible. And that's because volcanoclastic materials like an ash weather much more rapidly than something like a basalt protolith due to ash's high glass content and porosity. So if we take an example of a model like this one from Bishop et al., you can see the duration of climate warming, or basically the duration of liquid water, that's required to produce a clay-bearing unit of a given thickness, assuming a 15% clay abundance and looking at different weathering rates. Taking a rapid glassy weathering rate from the terrestrial literature, which would be similar to what we would expect for a volcanic ash, this model indicates that for the thickest aluminum phyllosilicate deposits we see, which were 130 meters thick in Nili Fosse, it would take about 3 million years to form. And this may be an order of magnitude faster than what you would need for a more crystalline basaltic protolith. I'll also note that jarosite is a metastable phase, so its persistence in the geologic record indicates that it likely formed in the last major phase of aqueous activity in these regions. So these kaolinite and jarosite units may be capturing the transition from wetter to more arid climates. Also, on the volcanism front, aluminum phyllosilicate may indicate more extensive explosive volcanism than previously thought, because explosive volcanism is the type that produces pyroclastics and ash. And explosive volcanism is expected to be more common on Mars due to its low atmospheric pressure at the surface, as well as the abundance of crustal volatiles. So it's been an open question why there's apparently limited evidence for it on the surface. However, much of this potential evidence is easily eroded, and so it wouldn't be expected to survive long-term in the geologic record. But aluminum phyllosilicate may be an indicator of these processes that has persisted in the record. And indeed, there is some purported evidence of explosive volcanism at volcanoes near aluminum phyllosilicate-bearing sites. Here you can see a map where the red dots show probable explosive volcanoes, and the black outlines are their probable pyroclastic deposits. I've added in purple the distribution of the aluminum phyllosilicate units. And you can see Arsia Mons, which is the proposed source of ash in Terra Sirenum. Patere and Arabia Terra could potentially source Marthalis, and Syrtis Major could be a potential source for Nili Fosse. If these aluminum phyllosilicates did form from volcanic ashes, then it suggests that explosive volcanism may be more common than previous geologic evidence indicates. And this could help resolve the question of its apparent scarcity. Additionally, these ash deposits appear to be more aluminum and silicon rich than your typical Mars-like basaltic compositions. And we're still thinking through what the implications of that could be for Mars's like interior processes. But if you have any thoughts about that, please find me throughout this conference. I would love to have a conversation with you about what that could mean. So in conclusion, in some areas of Mars, we find that aluminum phyllosilicate formed from an aluminous and siliceous volcanic ash, not as part of a weathering sequence. These aluminum phyllosilicate units likely represent a few million years of aqueous activity that largely ended with the formation of jarosite. But we note that differences in regional mineralogy indicate variations in protolith and fluid compositions, and that this analysis is ongoing. And further analysis of these and other regions, including Valles Marineris, Libya Montes, and Hellas Planitia, will be conducted. With that, I'd love to answer any questions that you have.
We do have time for a few questions.
Hi, Samantha. Thanos Kladaris from Purdue University here. I thought one of your northeast sites, you pointed out what looked like a really compelling unconformity between the FEMG stuff and the aluminum stuff on top. I was wondering if you've measured the dip of that contact, because I think that would be quite persuasive in favor of your argument that there really is a temp.
Yeah, it's a good question. I would definitely like to. We attempted previously with the CTX imagery that was available, and you couldn't. Unfortunately, there just wasn't that we have good enough resolution to be able to do that, because I think it would be interesting to be able to get that contact, if the geometry of that contact, if it's possible to do with a given exposure.
Fantastic, yeah, that'd be great.
Cathy Cantanata, University of Lyon. I do have one question. This kaolinite in topographic low, like in around Jezero craters, do we have locations that may be reached by Perseverance?
Yeah, there are some locations that could be in the crater rim. I think there's a couple of Breccia blocks that are kaolinite rich, and I've heard that it's possible as part of the crater rim campaign that they may be a potential target, which I think would be.
Yeah, but we have we don't know if it is exactly the same context, because it is within this mega breccia. The main point, do we have location where we have this topographic low with kaolinite?
I don't
in the
think
playground.
Yeah, I'm going to see if I can go back to my little regional map. No, I think unfortunately the closest ones are going to be those crater rim ones that could possibly be reached by. So these are the two locations that are in the crater rim. So I think these are kind of the only two that could feasibly be reached by the rover. This one here is not in a topographic low, and it's a little bit further away. So unless the rover is going to really make a long run of it, I think we're probably, unless we find something. Of course, there could be kaolinite that we don't see from orbit, smaller deposits that aren't visible from orbit. But in terms of the large ones that we see on the CRISM scale, unfortunately, I think these are going to be our only two locations that it could reach. But I would love to see some rover analysis. I think that would be able to really conclusively answer some of the questions that we have about them.
And also, Perseverance saw a lot of floats within the craters that are enriched in aluminiums. Some of that are kaolinite, also bearing rocks. But we don't have the context of those, but it means that we have in the watershed of Neretva Vallis some of these rocks we may miss, so you may be interested in this study.
Yeah, I'm really interested in those. I know there's been a lot of analysis that's been done in papers published out of the group at Purdue about those, as well as others. But yeah, I think that those, if they are the same rocks as the ones in Nili Fossae, potentially we got more of an up-close look. I know there's been some interesting results, like nickel, enriched in nickel, which could be an ultramafic origin. Nickel is also enriched in volcanic ashes. Sulfur wasn't detected, but also I know the methods weren't particularly meant for detecting sulfur, so it had a pretty high threshold of detection. But getting more rover analysis of it, I think, could answer those questions, in situ especially.
Thank you. Brian E. Horgan, Purdue. I actually wanted to ask about exactly this slide. So I'm intrigued that you have these, you've separated these into both the kind of plains and plateaus versus topographic lows. So do you see the same properties, same relationships, all those in both of those sets?
Yeah, we see some differences. So mainly the thing is, one of the differences is just the size of the deposits. All of our larger deposits are in these topographic lows at around the 50-kilometer scale. we looked at like what is the relationship of topographic lows at different scales. So the main thing is the larger ones are all in the topographic lows. We only see kind of like small exposures on the plains, and unfortunately, a lot of the exposures in Nili Fosse are good enough to get thicknesses or contacts. But jarosite as well we're seeing in the topographic lows primarily, with the exception of some on the let me use my mouse. We see some on the edge of the fosse, like on the slump blocks. Besides that, they're all in the topographic lows as well. All of the best kaolinite detections, like the most crystalline kaolinite absorptions, are in the topographic lows. But besides that, it seems to be fairly similar in terms of the mineralogy. We're seeing kaolinite everywhere.
Are you confident then that there isn't a transport relationship between the two? That the topographic lows could be detrital sediments removed from those plateaus and put down there, perhaps explaining some of the layering and stuff?
That's what I think it is, that it is this transported sediment that we're seeing, basically an airfall deposit that has been reworked and concentrated in the topographic lows. So some of it has remained on the surrounding intercrater plains, like ashes will sinter very quickly so you can get some that remains in place, but that it has largely been accumulated in these lows. What we're seeing the reason why we're seeing large deposits, thick deposits, are because it's like the enhanced effect of what fell there and then what has also been transported in, producing things like layers.
Reminds me of the painted desert, yeah, Arizona, right? Very similar.
Yeah, there's some good altered tephras in the southwest that seem to be a good analog for some of these.
All right, thank you. It's the end of that session. So now it's coffee break. So let's thank our speakers again. Okay, so we start again at 11. Thank you.
All right, welcome back. So I'm Erwin Dehoek and from the University of Lyon, and I have the pleasure to chair this session. So we will continue on the theme of early Mars environment with more intriguing observations and scenarios. And our first talk is by Olivier Bessac and collaborators on mineralogical evidence for pre-Noachian and Noachian surface liquid water in the Black Beauty meteorite and rover data.
So thanks, Erwin, and thanks to the organizers for giving me the opportunity to present this work, which mostly derives from the work of Virgil Malarevics. So the question I would like to discuss is what are the possibly new evidences for the presence of liquid water at the subsurface or surface of Mars in the Noachian or pre-Noachian. And for this, I will not talk about phyllosilicates, but I will discuss about quartz. And a bit about zircon, which is a zirconium silicate. And both minerals are really pretty common on Earth, but they are pretty rare on Mars. So just to start, I would like just to remind you that quartz can be magmatic or can be hydrothermal. But in any case, it generally needs water to form. I put two examples here. One on the left is coming from our beautiful mineralogy museum here on the campus. It's just next door. So we will try to organize a visit there. So if you're interested, just come and see me. It's just on the campus here. So it's a nice example of this hydrothermal quartz. And on the right, you have an example of quartz in a granite. If you want to see granite, you just have to walk in Paris. Don't look at the monuments. The monuments, they are in limestone. But if you look below your foot, Most of the pavement of a sidewalk in Paris is done with various granites, and you will see the quartz as the small gray translucent grain here. So quartz is really the emblematic mineral of the Earth's continental crust, and I will show you that we found it recently on Mars. And on the right, I represented zircon, which is among the most resistant mineral we have. It contains uranium, and it is used for dating with various radiometric techniques. So let me start with this general sketch about the geological evolution of various planets here. So if we consider the Earth here, the oldest rock we have for the Earth is coming from the Acasta gneiss in Canada. Is dated at 4.1 gigayears, but we do have some older geological records from single minerals, zircons, coming from Jack Hills in Australia and dated up to 4.3, 4.4 gigayears. If we go to Mars, Perseverance is exploring, as we saw, Noachian or Noachian to Hesperian terrains. But we do have some older record from the Black Beauty meteorite. Black Beauty is the nickname for the Northwest Africa 7034 or Northwest Africa 7533 meteorite, which contains zircons with ages up to 4.48 gigayears, but also a small fragment of rock with the same age, which means that Black Beauty is really a unique rock because it gives us access in the lab. We can play it with the lab instrument. It gives us access to the first 100 million years of Mars, and this is something we do not have for Earth, apart the small zircon grains. So I will start with this recent paper coming from the SuperCam team on board Perseverance. So Perseverance, exploring a J0 crater, found some light tone float rocks represented on the right, mostly on the margin unit and on the crater rim. And we did some leaps on some of these float rocks, and the leaps indicated that these rocks are composed by pure silica. We did some Raman spectroscopy on the one delineated in black in below here, like the Emmons Glacier target. And we found a spectrum like the red spectrum here, which is compared here to the spectrum of hydrothermal quartz crystal in the lab. And this is really a fantastic data because Raman on Mars is a tricky thing. And you can see that we have all the expected mode band for quartz, indicating that this quartz is very highly crystalline. And this, and considering some textural argument, we ended up with a conclusion that it is likely hydrothermal. We found some other light tone float rocks that we studied with the infrared spectrometer of SuperCam. And these are typically the green spectrum from the Elves Chasm target here, with 1.4 and 2.2 bands. And this spectrum is compared to the desiccated Opal A spectrum in the lab. Consistent with this, you have another target, which is the Aegis target in blue, which is consistent with Chalcedony. And these two phases are amorphous to microcrystalline phase of hydrated silica. So we interpreted all these phases to be formed in a hydrothermal system, which is depicted on the right, where you have water, surface water, percolating through fractures. Going at depth, it can dissolve some rocks, then transport some silica, and for any reason, a change in the fluid composition or a change in temperature, it can precipitate and saturate in silica. And depending on the depth, it will be quartz at depth, and it could be chalcedony or opal at more shallow levels. So this hydrothermal system was likely triggered by the J0 forming impact, so it's likely Noachian. And what is interesting is that Perseverance found other evidences for hydrothermalism, or at least it was interpreted as due to fluid interaction, like the aluminium-rich float rocks described in a paper by Royer et al., but also serpentine described yesterday by Cathy. In any case, for all these rocks, we need subsurface to surface meteoritic or liquid water to form these minerals. So now let's go to Black Beauty. At least there will be one meteorite in this meeting. So this is a beautiful meteorite. You have a section of a meteorite here. You have the scale below. It's a centimetric section. And this meteorite is a breccia, which means that you have small fragments of rocks, which are emphasized with a white dashed line here, which are embedded within a crystalline, microcrystalline matrix. On the right, you have a compilation of age for this meteorite. This is one of the most dated rock we have in our labs. And what is interesting is that if you look at the red edges, which are coming from the clast, the zircon edges, uranium-laid edges, but also the samarium neodymium age for the wool clast, they all cluster at ages from 4.3 to 4.4 gigayears. So recently we investigated a new section of this meteorite, like the one here. Again, you have the scale, and we found a peculiar melt zone, which is depicted on in the middle here. You have a chemical composition map, and this zone is enriched in calcium, depleted in magnesium, and we found some silica-rich hotspot in this zone. So we went to the lab, we did some Raman microspectroscopy, and we were able to show that these grains are composed by quartz. You have the spectra here on the right. We did also some transmission electron microscopy to look at possible shock features in this quartz. We did not find. So it's really, again, highly crystalline quartz. So what is interesting is that in this meteorite, quartz can be detected as single grains, like the He figure here. You have a fragment of a larger crystal of quartz, but it is also often found within fragments, within clasts, with other minerals. And these clasts include the quartz. They can include, as you see in the middle, with a chemical composition map. It can include K feldspar, plagioclase, ferromagnesium mineral, which is in general pyroxene, and phosphates. And this is typically the mineral assemblage of a granite. If we look at the bulk composition of this clast, you have a classical geochemical diagram, which is the total alkali silica diagram here on the right, representing the alkali versus the silica content. So I put a compilation of Martian data. In blue, you have the shergotite, knackite, chassinite series of meteorites. In green, you have the data from Curiosity at Gale Crater, showing a nice trend in the magmatic differentiation from basalt to trachyte, and you have a similar range of composition in the other class of the Black Beauty meteorite. And if you look now at this new class, they are depicted in yellow, and they really fall into the granite field here. So what is interesting is that these clasts are really the most evolved magmatic rocks identified from Mars so far, and they are Pre-Noachian. They have an age older than 4.3 gigayears. So what about water? So we tried to estimate the temperature of crystallization of this quartz in Black Beauty, and for this we did titanium in quartz thermometry. This is a challenging exercise because the quartz grains are pretty small. You have to use an ionic microprobe because you go to very low concentration here. And you have the calibration curve represented in the pressure-temperature diagram here for the obtained titanium concentration. So if you assume a present-day crystal thickness for the Martian crust, you end up with temperature of crystallization in the range from 650 to 850 Celsius degrees. On the right, you have another pressure-temperature diagram showing you the solidus curve for various lithologies, granite, basalt, or peridotite. On the right, you have the dry solidus in the absence of water. So it happens at very high temperature, above 1000 Celsius degrees. But if you put water in the system, you will have a wet solidus, and you will shift the curve towards low temperature. And it is represented here again for the three lithologies. So if we put the estimated temperature for the quartz crystallization in this pressure temperature diagram, you can see that whatever the rock precursor, the protolith of a clast is, we need the temperature for melting is possible only if the solidus is shifted to lower temperature due to the presence of water. And we need to have a magma saturated in water to melt the rock here. We can go further about the action of water on the formation of this quartz. And to do this, we can look at the isotopic composition of this quartz again using ionic microprobe. And this is represented here in the top for the delta O18, the oxygen 18 isotopic signature, and the delta silicon 30 with the blue square. So they are compared here to a selection of terrestrial rocks, but also to the bulk composition of SNC meteorites, or the bulk composition of the terrestrial mantle indicated by the morb here. On the right, you have a compilation of data for oxygen in the middle, showing you that most data are clustered about 5 per mil. And if you want to go to values, as we observed in the quartz, in the Black Beauty meteorites, which are pretty high value, up to 10 per mil, you really need to consider that this quartz derives from the melting of rocks, like sedimentary rocks, or rocks or minerals that were in contact with liquid water. It's the same for the silicon on the right, where you have a compilation of silicon of the delta 13 silicon for various quartz on Earth. Against all values are clustered about 0 per mil, and only if you go to quartz in contact with liquid water, like in sediments, or you have the value also for the seawater and so on at the bottom. The only explanation we have to explain such a high value we observe in Black Beauty is to consider that it's coming from the melting of such a protolith. So in any case, the protolith of a quartz-forming melt must have interacted with liquid water at low temperature, it's important, prior to the melting, which means that we need to have subsurface, surface alteration, aqueous alteration before the melting, so before the 4.3 gigayears. So I will finish with this message, is that 2025 was a good year for quartz on Mars because we found these two new occurrences. It can be hydrothermal, like we found with Perseverance, or magmatic, as shown in the meteorite. We have the first occurrence of granite on Mars, and it's dating from the Pre-Noachian. In any case, we need liquid water at depth. To do the quartz, the magmatic quartz, but also in the subsurface or at the surface to do the hydrothermal, or to have the protolith for the granite to do this quartz. And in that story, impact in both cases provided the extreme geothermal condition for melting, because you need to have very high temperature at very shallow level to do, for instance, the granite in this rock, and it triggered the advanced magmatic differentiation. So I put this diagram, which is one recent publication showing how understanding about the formation of Akasta gneiss. There is some stuff. There are some similarities with what we could infer for Mars. There might be some differences too, but in any case, it's interesting to see that we have similarities between this rock. And I will stop.
Thank you very much, Olivier. We have time for questions. Oh, I see there is already one. Go ahead.
Bethany Ellman, University of Colorado. Thank you for coming to give this talk, because I think it's one of the more interesting finds on Martian meteorites for a very long time.
Thank you.
So super cool. 2 questions, one simple and one maybe more complicated. The first question, which is simple, and you were maybe talking about it on the left, but when we look at the oldest rocks, do we see these types on Earth? Do we see these types of clasts, noritic clasts, monzonite clasts, quartz clasts, or is this actually that these clasts are this old on a planetary surface is itself unique?
So, I say class because these are small rocks within a meteorite. Yeah. So if I go on Earth, for instance, if you go, you mean in an environmental of impact rocks on Earth? Or?
It doesn't, no, I don't necessarily mean an impact rocks. I just simply am ignorant of in rocks that are like greater than 4.3 billion years old, what the prevalence is of those fragmented rocks like monzonites and norites and quartz-bearing clasts. Do we see anything like that?
The only thing we have for such
at any scale.
No, the only thing we have are these small zircon grains for this age on Earth. And if you look carefully in some of these zircons, we can find inclusion of K feldspar, but also of quartz, which suggests that we may have the similar lithologies at this age on Earth. But again, the only rock we have are the Acasta gneiss at 4.1 gigayears, and in fact, the composition, I did not put it in the TICE diagram, but it's pretty similar to the composition we have for this class here. And again, if you look at the series of differentiation in the Idiwawa gneiss in the Acasta, you may have a similar trend in terms of differentiation from norite, monzonite, and then granite.
Okay, that's helpful, thank you. And then to your later point about that, the parent material had to have interacted with water prior to eruption. I understand the isotopic arguments for that. Does that also mean that there was sort of that the alteration caused any bulk chemical fractionation, or no? There's not any implication for the bulk composition of the rock?
No, it's really about the quartz here. So these are in situ measurement in the quartz grains. So you have this value, pretty high values, and the only way we can explain these values is to have the quartz crystallizing from the melting of something that was enriched in oxygen 18 or silicon 30 here. That is the implication, not about the bulk rock, but really about the quartz here.
Okay, got it, thanks.
Oh yeah, Brandy Horgan, Purdue, really interesting. I wanted to ask if you, relative to Bethany's question actually, have you done any comparison to the granitic clast and lunar meteorites? Because those have spawned all kinds of petrology work on the moon for how you evolve materials in a non-Earth.
In other Martian meteorites, there are small pockets of granitic-like composition, but coming from the extreme fractionation locally of magma. These are really small in some chagotites. And then if you go to other meteorites, the only meteorites where you can find such things are lunar meteorites, or also some lunar breccia from Apollo missions. But you don't have exactly the same lithology and the same mineral assemblage. It's simpler than this one, so I'm not sure it's corresponding to this kind of global differentiation.
All right, let's thank Olivier again.
So just, Erwin, so if you want to visit the mineral collection, I will try to organize something. You just come and see me. It's just on the campus here.
Really worth it. All right, we'll move on to the next talk, which is by John Carter and collaborators on the question, was Hellas planitia a Noachian sea?
So good morning, everyone, and thanks, François, for organizing this awesome conference. Here we have a little conundrum regarding Hellas planitia, which I wanted to talk about. And so first, I apologize for those who attended my talk at Caltech last year. Progress has been incremental since then, which is a very polite way to say that it's very, very, very slow. So we want to study Hellas because, well, Hellas is a relatively understudied area of Mars in terms of surface geology and mineralogy because it is hell to observe. Really, it's very difficult to get good data of Hellas planitia, which is one of the reasons why progress is slow around this basin. But it's an insanely interesting basin. It's very old, early Noachian, and as such, it has accumulated signal from geological processes since the Noachian, and it was also likely a sedimentary sink when Mars had a form or several forms of hydrological system, whatever their duration. So this is one of the main drivers for the study, and this HRSC image shows you how hard it is to study Hellas, because when it's not covered by frost, it's covered by haze, and when the haze is gone, then dust storms arrive, and then frost comes back. And so you only have very small windows in which you can do some good, meaningful compositional sensing in particular. And so Hellas was once much deeper than it is today, but it was largely infilled by a number of mass wasting processes, and in particular by lava from the late Noachian and early Hesperian processes, and possibly also by ice deposition and transport, per a recent paper with Jim. There are unique terrains in Hellas Planitia, which are called the banded and honeycomb terrains, and you can see some nice examples on the right. As you can see, they have these sort of shell-like structures. These are the honeycomb terrains, and then you have these sort of viscous flow features, which are called the banded terrains, which usually occur around topographic excursions over the Hellas floor. And these terrains are mostly located in the deepest parts of Hellas Planitia. As you can see in the topographic map, we are talking about the northwestern part of Hellas. We're not on the margin. We're really low in the lowest reaches, minus 7,000 meters. So it's the deepest parts. There is an ongoing debate as to if there is a genetic link between these two types of morphologies, which are close by and sometimes sort of intertwined. And so the understanding is that this area is so deep because there is this sort of wind corridor that has consistently eroded terrains over very thick amounts of strata since the Noachian, actually. And so this is exposing very deep material in the Hellas floor. So it's been recognized that from past geological mapping from several groups that these terrains are partially, as I mentioned, intertwined. These are mapped in the left here, and these correspond again to the deepest parts of Hellas. And an analogy has been made, well, several studies actually, but as you can see here on this Hellas 3D view of the Hellas honeycomb terrains in the top versus what's in the Gulf of Mexico. In the bottom, you can see that these structures resemble, there's a change in size, there's a ×3 difference in size, but obviously we can see the same sort of cell-like structure, and it's been shown that these are likely salt diapers. Well, these are for sure salt diapers in the Gulf of Mexico, and by analogy, it could be that these are salt diapers, but this was never really conclusively demonstrated. And so these diaperitic terrains of Hellas have been studied by a number of groups before us, and we're really basing our work on this excellent pile of literature which has been done, and explain with I think good certainty that these are indeed diaperitic terrains. And I'll refer in particular to the rather recent paper by Weiss and Jim, where they really looked at the terrains and tried to model what this means in terms of what's the underlying terrain that is uplifted as per the diaperitic process. So there are basically two contenders. Are these salt diapers or are these made of ice? Both could work, and models developed to explain this well. And obviously ice would make sense for a number of reasons for Mars. And so we looked at the mineralogy. So this is a topographic map of the western part of Hellas. In red are there are detections of iron magnesium smectites and friends. In cyan are detections of silcrites of opal, of hydrated silica. And in green, which are the main interest of our study, are the polyhydrated sulfates. And you can see that there is this really nice zonation. It really looks like a first-year geology textbook of what's in a basin that dries up. You have marginal clays, and some of these are known. Some of these are weird or hydrothermal or uplifted, but a number of these are sedimentary in nature, including in paleo lakes. And so they're in the upper parts of the margin. And then as you go down, you have the largest opal deposit on Mars, which is probably a silcrite. It has some weird, funky, highly acidic phases inside also, but it's mostly opal, and Maxime is working on this, Pino. And in the bottom, as I mentioned, are in the lowest parts, this sulfate. And you can see on this topographic histogram that there is clearly a vertical zonation of the different phases. And so let's zoom into this very low part and deep, let's say deep part of Hellas. And here are our sketchy and kind of shitty detections that we could make out after a month of hard work. And we do see this sort of peppered green stuff, which is the sulfate detections based on Omega and Chrism, multispectral and targeted mapping. And you can see that the sulfate is mostly in the sort of this diagonal on this image. And if you correlate this with the location of the honeycomb and the banded terrains, both of them, not just one of these terrains, you can see that their correlation is not perfect, but it's very good. It's not quantified yet because we need to take into account scarcity and signal to noise, but basically, we can see that it correlates well, and when we have good data, we see that there's a very sharp contrast between the geology and the mineralogy. So we have a very, very good correlation at 20 meter per pixel resolution between mineralogy and the banded and/or the honeycomb terrains. Here is the same with just a topographic map, which shows you in the dark blue contour that we're really only in the lowest part of Gilles northwestern floor, and some images are showing you the sort of sharp contrast that we can see, although the image, again, both image quality and mineral quality of the maps are sort of underwhelming compared to other areas of Mars per the issues I've mentioned for observing Gilles. We've made a cross-section of these salt deposits over the banded terrains, assuming that we can state that the banded terrains and the honeycomb terrains are salt-rich. And so, as you can see in this, well, the central image in orange outline has this butte, and it looks like a small butte, but it's not a small butte. This is a 1.25 kilometer high butte, which is probably a remnant hill, which tells you a story of intense erosion that has probably removed over a kilometer of material, which has, per previous study, is overburdened material which has been removed. But so we can expect that there was a kilometer of material which was removed, which is what you need to have overburdened material to have diapers. And below this, per the range of elevation that we see and per what we know of the correlation between cell size and depth for diapers, we expect that if we indeed base our observations our hypothesis on the observation that these are indeed sulfates, then these diapers are a kilometer thick, at least, of salt. We do not see the base because we lack, unfortunately, a good stratigraphic window, but let's say we have a kilometer-ish of sulfates, which was probably buried under a kilometer-ish of material, as observed today. The mineralogy itself is pretty boring. In Chrism, this is our usual sulfate, polyhydrated, unconstrained magnesium, probably, or Ca sulfate. It's sort of the same throughout the floor where we can get the good data. Looks very much also like the basal sulfate deposits of the Turby Paleo Lake. And again, we don't have a strong constraint, but they're presumably a polyhydrated Mg or a Ca sulfate. Maybe some wiggly lines could be some presence of jarosite or gypsum, but it's honestly we can't really say for sure, as is often the case. And so in this excellent paper from Weiss and Jim a couple of years back, they made this model where they looked at different material and tried to constrain with the model how what material could explain diapers according to, one, the overburden thickness, and two, the thickness of the actual material, which is deformed, and so the lower density material which goes up through the process. And so the conclusion was that it could be ice or salt. There is very good reason also to suggest that ice is probably the main contender based on the model and geological evidence, but our take on this is that we think we could have the other solution. If we look at the densities that were used in the paper, they assume the halide gypsum of kieserite as the salt contenders, and we think that what we're seeing is probably sulfates which have a slightly lower density, which would make it easier the diapers to come up. And so we think these are actually good candidates to form diapers. These sulfates, whatever exact composition they have. They would form diapers. So in summary, we observe that up to a kilometer of overburden material existed, and we observe what we think are over a kilometer thick of salt at the floor of Gilles planitia. So in terms of implication, there's this really nice paper. I really love citing this paper from Ralph years ago now about the missing salts paradox. And this is a really simplified version, a vision of the salts during the Noachian, but you could sort of dumb it down to three main scenarios as to why are we seeing so few Noachian age salts. So maybe they were never formed. That happens in a very acidic climate. where they only form in place and volumetrically not so much. Or it was icy, so mostly the alteration was subsurface. Or they were dissolved and they then were reprocessed in the hydrological system, and then perhaps the Hesperian salts were Noachian salts before that. Or we haven't observed them, and this is one of the cases we like to make, is that it's probably a combination of many scenarios, but we have, I think, collectively neglected the fact that if the climate was more humid, salts would form at a distance through runoff, ponding, precipitation, and they would form in the oldest and most infilled or degraded basins on Mars, in sedimentary basins. And so there's probably a detection bias in the fact that we rarely have access to well-preserved Noachian age, the bottom of sedimentary basins that are Noachian age. And here we see the deepest parts of the Noachian age Helix basin, which are possibly, we think at least, covered in a kilometer of salts. End-member scenarios. One end-member scenario could be the Messanian salinity crisis of the Mediterranean, which many of you probably know of, which is when the Mediterranean closed up and it dried up, mostly dried up. And as a result, most of the current seafloor deposits in the Mediterranean are kilometers thick of gypsum and halite. This is when we were drying up the Mediterranean, and then it flowed back in catastrophically, but then the water is still, the salts are still there. There are mild variations around this scenario today, as it is understood for Earth anyways, but this would mean that at some point we had an ocean in Helix Planitia of kilometers thick, and then there was a shift from wet to dry, as is expected, and then the ocean dried up, and we have these remnants, salts evaporating. Another scenario is closer to the recent paper by Festook and Jim, where we have this ice sheet which probably accumulated with basal melting and transport, and then you have a huge amount of ice which is either in form of ice or melted at the bottom of Helix, and then this could transform in salts. And finally, our last intermediate scenario would require occasional lakes which would accumulate little by little salts over time, which is hard to test. So I just want to stay with our conclusions. We think we found a kilometer's worth of Noachian age salts, which likely require the hydrosphere to form. We think these Helix Planitias are indeed salt diapers. We are still looking at it. Maybe a sea, maybe a succession of brackish lakes. But anyways, it has really a strong potential, we think, for climate modelers to provide an anchor point on the climate of early Mars, if indeed we're able to confirm the exact nature of this water deposit. And thanks, sorry, I was a bit long.
Thank you, John. Questions? Go ahead, Jim.
Jim Head, Brown University, really excellent treatment, and it's a complex problem. I really like your advancements on it, okay? But I just got a text here. Apparently President Trump is live streaming thing, and he asked me to remind you that it's the Gulf of America, not the Gulf of Mexico.
Thanks, Jim. Yeah, and probably Helix Planitia should be renamed something more patriotic, I agree, yeah. There's plenty of open land to rename on Mars, so yeah. Nice potential.
You get to pick the name. One question is, we know sulfates will be dirty. How pure much a deposit be way to trigger diaperism? Have to be like nearly pure? And does it about that mechanism enough?
It's usually fairly pure. I honestly, I forget a little bit now. It's been a while, but it's mostly a question of density, right? So if your rock, in the end, you're forming a rock. If your rock is a low density, it can form the diaper. So if the sulfates are weighted down by highly dense material, it's probably not going to work as much. So it's going to be probably a degenerate problem between the amount of sulfate and the density of the other stuff you're mixing the sulfate with. I mean, from terrestrial diaperic terrains, such as the Gulf of Mexico or the Dead Sea or Iran, I mean, the salts are pretty pure. But these are formed in the evaporating body of water where you're sort of, it's the Dead Sea, you're forming salt. It has inclusions, of course, usually there's the nucleation site and then the formed salts, but it's mostly evaporating salts, simple system. That's a planetary science view. It's always, we simplify things, but it can be pretty rich in salt. But this supposes that we have a standing body of water that evaporates, and we could have something that maybe is a little more Mars-like than that. So no clear answer yet, but yeah, thanks.
The sulfates we found at Guerre are pretty enriched. Exam sulfate.
In diaperic terrains on Earth, you have these salt terrains are salt. I mean, they're mostly salt. It could be consistent with over 50% for sure. Yes. Yeah.
I think it is. A quick one.
Question. Lonneke Roelofs from Utrecht University. I was thinking about the second hypothesis that you proposed to get these salts there, which is the glacial one. I was just wondering if you could elaborate on that one a little bit, because I don't see that in my head, but maybe because I miss an Earth analog.
I wish I could. I mean, I mention it because it's been well modeled by well, there's a pile of evidence that there was a huge glacial imprint, especially on the eastern part of Hellas, and the works by James Group and others have demonstrated that it's highly likely that there was a huge amount of ice which accumulated. We're talking hundreds of meters, kilometers of ice that could have accumulated and melted at some point. So it means there is a source of water, and this water, if our hypothesis is these are not ice diapers, they are salts, so this water was removed from the system at this point. So either it evaporated or it's sublimated at some point. There is this wild idea these days that we could form sulfates by what we call sublimites. It's a kind of weird process, rare process, where when you're sublimating your water, you can form some gypsum, for example. But how to scale this at this scale, I don't see how it's possible. You could have other processes, more like what's been proposed for Meridiani Planum, of what we're proposing for the south of Mars, that you have your dirty ice, which have sulfur in the grains, and as the ice melts through episodic melting, then little by little you're enriching in sulfates. Honestly, to me, this is harder to explain a kilometer of salt, and I wish we had the good stratigraphic section into the diapers to be able to see if the salts, if there's something that is really dirty, or that is something that is mixed or not and stratified or not. I don't think we'll ever have that answer.
Could it be after each other? So you have a standing body of water first and then the big glaciation event? I don't know about the chronology.
Jim would know that better. Yeah, I mean, presumably there was more water. I mean, presumably, yes, we know that there was a standing, I mean, there was most likely that there was a lot of water at some point to explain the other features that we've heard about today and what we know of, and at some point there was also glaciation. So both are possible, but the exact processes by which we're able to concentrate a kilometer of salt from ice or just from melting, I don't see it at this scale, but I think there's work to be done there. Yeah.
Okay, thank you.
All right, thanks very much, John, again. We're going to move on to the next talk by Margaret Dean on hydrothermal systems on Martian crater rims.
Hello, I'm Margaret Dean. I'm a PhD student at Purdue University working with Briony Horgan. And today I'm going to be telling you a little bit about some work that Briony's postdoc Lingqi Zhang has recently published on for Ritchie Crater, as well as some preliminary results from the what's to become the second chapter of my PhD, focusing on hydrothermal systems on Toro Crater's rim. So when a hypervelocity impact strikes the surface of a planet, it can create, the energy from the impact can potentially create an internal hydrothermal system localized where this crater is. And so this is a really beautiful figure by Ozinski et al., published in 2020. And this kind of shows the materials that may form as a result of an impact crater. We have a lot of terracing and some brecciation going on where these fractures could potentially be pathways for fluids. And then the heat generated from the impact can also create an environment where that could be habitable and that thermophilic organisms may thrive in. And so that's what we're seeing over on the right here, is a potential localized hydrothermal system that could exist. So when we're looking for evidence of these hydrothermal systems, we specifically want to look for alteration products. More data, though, is needed to constrain these alteration products' generation and duration. Previous studies have focused on the central uplifts of craters, but alteration minerals have also been detected in the crater wall to rim region. So on the left, we have the Toro crater central peak. This was a really comprehensive study of Toro done by Marzo et al., where they mainly focused on the central peak region, and they found both low temperature and high temperature alteration minerals present in this central peak that may be indicative of some sort of hydrothermal alteration. On the right, we have a figure from Ling Chi's paper on Ritchie crater, where he focused on specifically the crater wall to rim region, and he also was able to find evidence of these alteration minerals that could be indicative of an impact-induced hydrothermal system. So the exact origins of alteration minerals in these wall-to-rim areas have remained quite ambiguous and have not been thoroughly examined. We can't just automatically assume because we see alteration minerals in the rim of an impact crater that they formed from an impact-induced hydrothermal system. That could be one of the hypotheses for these mineral formations, but the other hypothesis would be that alteration minerals may have been excavated from pre-existing altered bedrock and or deposited by later fluvial lacustrine processes. And so one thing that we're looking for is evidence of these alteration minerals that are specific to the rims of these craters. And so what we're looking at here is we're assessing how crater size, latitude, and age affect the presence of rim hydrothermal systems in Martian complex craters. On the left, we have Ritchie crater. It's a 78-kilometer diameter crater located south of Valles Marineris. And on the right, we have the other focus of this talk, Toro crater, which is about 40 kilometers in diameter and located on the northwestern edge of the Isidis Basin. So here we report the clearest example that we found of impact-driven hydrothermal alteration on a crater rim to date at Ritchie crater, and then our preliminary results of similar investigations on Toro crater rim. So the most common impact-type stratigraphy seen on the rim of Ritchie crater is comparable to lithologies that we observe in complex craters here on Earth. And so on the left, we have the Mars Ritchie crater figure. And what we're looking at here is on top, we have this sheet unit. It's this smooth, flat, coherent surface that we interpret to be some sort of melt-bearing breccia that is splashed over the edge of the rim of the crater during the actual impact event. Beyond the smooth surface, it also appears to have some sort of brecciated slope associated with it as well, likely created during the impact. Underneath that, we have the brecciated unit, which we interpret to be a melt-pore breccia that was originally ejected when the target rock was struck. And this typically appears to be a lighter toned and fragmented. And then lastly, Ling Chi identified an altered basement unit, and these are light toned fractured materials, and they often have ridges in them as well. And then on the right, we have a comparison to Reese Crater and Mistassini Lake on Earth. We have a polymictic breccia, which is part of the ejecta blanket that form Reese, and then we also have an overlying melt-rich breccia versus swavite type material associated with impact melt. So we are seeing these types of lithologies both on Earth and on Mars. Next, I'm going to walk through the composition of these units. So the three candidate impact units show distinct spectral properties. At Ritchie Crater, our sheet unit has a absorption at 0.9 micron that we typically associate with the presence of low calcium pyroxene. And we also see potential evidence of olivine or glass. And one thing to note is that this particular unit is unaltered. We don't see the presence of any sort of alteration bands in the spectra. Next, we have the brecciated unit. This unit is typically olivine or some sort of glass, and we see minimal hydration. And this is typically underlying the sheet unit. And then lastly, we have the altered basement unit. Lingji has several examples of spectra taken from the altered basement unit here, and we observe strong and variable alteration signatures. We have some potential Fe-Mg bearing phyllosilicates, but we also have spectral bands that may be representative of Mg carbonates as well. So at Ritchie, there's clear alteration observed in the underlying basement rock where it's in contact with the impactite stratigraphy. I believe Lingqi did a much more comprehensive look, even outside the crater, for basement rocks that aren't in contact with this impact melt, and did not observe the same levels of alteration that we see here where it's in contact. So we interpret this to then be evidence of hydrothermal alteration associated with heat from the deposition of this impactite melt onto the basement materials. This is a beautiful figure Lingqi made, where we propose that the diverse alteration minerals in Ritchie Crater's rim track the evolution of a hydrothermal system following the cooling of the impact melt. So I'm going to start in the box from the left there, labeled B. We have here the kind of basement materials. The peachy color is the ejecta that was originally ejected out when the target rock was struck. And then on top of that, the orange is an impact melt. And all of these materials have a lot of heat, and what they do is that heat then can trigger the convection of water and create this saturated zone from the water table. And what that does is that then alters this basement, and it may create a environment where that could potentially be habitable, where we might find biosignatures. Another thing I wanted to point out on this diagram is in our 3D version, what's closest to you is our central uplift, and that typically has the highest temperatures during impact. So we expect to find high temperature alteration minerals, and then there appears to be a gradient as we go closer to the rim, where our low temperature alteration is probably occurring closer to the actual rim, which is more conducive for life. So we aim to build a catalog of complex crater alteration minerals present in Northwest Isidis crater rims, following this model for later comparison to Jezero's rim. So here we are investigating candidate impactite lithology on Toro crater as an analog for the similarly sized Jezero crater, but Toro crater is much less degraded. For my first PhD chapter, I mapped the rim of Jezero crater, and it is a very degraded crater rim. And while we still see a lot of diverse materials here, Toro has some really pristine exposures of candidate impactite materials on its rim. And so in the blue, we have the fractured unit. It is blocky, fragmented, and light-toned. In the green, I've pointed to the modeled unit. It's rugged, patchy, pitted, and very dark-toned. And then my purple is the smooth unit. It's smooth, it's flat, and it's intermediately toned, and it occasionally retains craters and evidence of other geologic activity. So the three units on Toro crater's rim appear to have a similar stratigraphy to those seen on Ritchie crater's rim. And so again, here's an example of our three units in relation to each other. Our blue is our fractured material, green is modeled, and pink is smooth. And then on the right, we have Lingqi's sheet unit, brecciated unit, and altered basement. And based on these preliminary results, what I believe we're observing is that Toro's fractured unit may be consistent with Ritchie's brecciated or altered basement materials. I would need more actual compositional data. That would be the next step here to actually determine which they're more likely related to. And then our modeled and our smooth units seem to be comparable to what Lingqi described as Ritchie's sheet unit with the flat top and the brecciated slope. So in summary, we observe evidence for alteration on Ritchie crater's rim in high-rise and in Chrism. This may be evidence of some sort of hydrothermal alteration associated with heat from the deposition of that impactite and melt onto the basement materials, thus generating convection of fluids throughout the system and potential alteration. The hydrothermal systems persisted beyond the central peak into the rim. So typically we focus on the central peaks of craters when we're talking about these systems, but we're suggesting that you can actually find evidence of these systems as well on the rims, and they would exist at a lower temperature than at that central peak and become more habitable much more quickly than at the more extreme temperatures that we're finding in the center of the crater. A preliminary look at Toro crater reveals pristine exposures of candidate impactite materials, so Toro may be able to act as an analog for Jezero, as these two craters are very similar in size, and Toro is younger and better preserved than Jezero is. And then lastly, subsurface low-temperature hydrothermal systems at crater rims could have provided a habitable environment outside of crater central peaks. So this kind of research has implications for potential habitability, and it's exciting that we are actually traversing around a crater rim and may be able to learn more about these types of materials. Thank you.
Thanks very much. Do we have questions? Betty running.
Thanks, Margaret, for your talk. I do have one question about Ritchie craters, because Ritchie crater is south of Valles Marineris, where we do have well exposed in the wall of Valles Marineris, the Martian crust, where we have evidence of hydrothermal alterations of this Martian crust. It is reported in Viviano Beck papers and other papers. How do you discriminate between excavated hydrothermally altered crust and impact-related alteration?
Yeah, that's a really great question. My understanding is that Lingqi really went and did a deep dive into the other bedrock within this region that wasn't necessarily in contact with impactite and found that it was not altered in the same way. So specifically where Ritchie is, I guess that was kind of what his observation was. Also, he observed a lot of diversity within the alteration minerals. And so I guess you would have to actually compare what we're finding at Ritchie to what we might be finding in Valles Marineris. But as I'm not the one that actually did that investigation myself, I couldn't give you more details than that. But he did publish a paper on it, so I do recommend that we go check that out as well.
All right, thanks very much. Thanks,
Thank you.
Margaret. Our next talk is by Bingshu Hu and collaborators on manganese hydroxide in Utopia planitia.
Hello everyone, my name is Bingshu Hou and I'm a PhD student from Peking University, China. And it's a real honor for me to have the opportunity to share my research with you. And today I'm going to talk about my recent research about the manganese, what the manganese tell us about aqueous environment on Mars. And the title is Manganese Hydroxide Record the Dynamic Evolution of a Millionaire Has-Been Ocean in Utopia planitia, Mars. And first, I will start with a brief introduction. So far, there's a significant body of evidence suggesting that Mars once had liquid water. For example, the positions of certain contacts on the surface are interpreted as potential ancient shorelines. Additionally, infrared spectra collected by the orbiter have shown the absorption features of hydrous minerals, further supporting the idea that water played a role in Mars history. Other features like rigid plains or pitted cones also support the idea of past water activity on Mars, such as valley networks and the Basin Lake Formation. However, despite these observations, there are still some fundamental uncertainties. For example, we are not sure about the volume variation and longevity of the water, or whether their presence was continuous or episodic. And this uncertainty is actually the main motivation behind my research. I'm majoring in mineralogy, and I plan to approach this research from a mineralogical perspective. And in this study, we are focusing mainly on the manganese oxide. Manganese precipitation is strongly linked to the dynamic aqueous systems, like the shallow lakes and coastal regions. During marine transgression and regressions, manganese gets oxidized to form manganese hydroxide, which then accumulates along shorelines. So because of this feature, I believe that the manganese hydroxide could provide valuable information about past water conditions on Mars. However, the detection and discussion of the manganese on Mars is still quite limited. And with respect to the study area, we are focusing on the Utopia Planitia, which is the vast basin located in the northern hemisphere of Mars. And the basin's surface is mainly composed of has-been VBF deposits. However, the deposition process and the environmental significance of manganese hydroxide within the VBF are not well understood. And the Chinese rover Zhurong landed in this region, and which provide us with a valuable opportunity to detect manganese hydroxide directly. So here I summarize the key motivations and objectives of this research. The motivation is to, we want to know the volume, variation, longevity, and continuous or episodic of ancient water activities. And the objective is by integrating short-wave infrared spectral analysis from the Zhurong rover in situ detections with remote sensing observations from Omega and analyzing the spatial and temporal distribution of manganese hydroxide. This discusses the evolution of the Martian water environment quantitatively. And next, I will talk about the datasets and the model we used. Our infrared dataset includes about over hundreds or thousands of simulation shortwave infrared dataset according to the HIPKey infrared model, and also over hundreds of laboratory shortwave infrared spectra of Martian soil simulants and Martian spectra collected by the Mars Code instrument on board Zhurong rover, as well as by the Omega orbiter. And based on this dataset, we designed a model, a deep learning model named Spectral Contrastive Aware Network, or we can call it ScanNet. And here I do not intend to explain the model details in depth, and here's our findings. The Zhurong rover traversed almost 2 kilometers southward from its landing site. Along this traverse, 4 types of geological materials were identified, which are soils, rocks, derricks, and TAR sands. And elemental analysis using LEAPS reveal pronounced peaks in the manganese doublet. In addition, the infrared spectra showed a broader absorption band of manganese hydroxide, and the concentrations of the manganese were then estimated with an average of about 4.5 weight%. And notably, the concentrations of manganese hydroxide exhibit a clear increase with altitude. And this trend mirrors findings from the Curiosity rover in Gaia crater, where such deposition has been attributed to oxidative diagenesis in aqueous environments. As you can see in the picture, the manganese hydroxide precipitation generally occurs in shallow surface waters, as reductive dissolution in the deeper conditions inhibits the oxidation of manganese, but can generate iron oxide. Based on the same trend observed here, the manganese hydroxide near the Zhurong landing site were likely formed in aqueous environments. And we also apply the ScanNet on Omega spectra dataset. We found high concentrations of manganese hydroxide primarily located near the basin rim and below the proposed shoreline. Previously, the Zhurong rover identified features near the lenticide interpreted as herringbone cross laminae formed by bipolar current directions. So we also found a spatial overlap between the manganese hydroxide and pitted cones, which is shown as the red dots in the picture. And these lines of evidence collectively suggest that the Zhurong landing area was likely formed in a nearshore marine environment. And we also observed a distinct temporal relationship between the abundance of manganese hydroxide and Martian geologic epochs. Area with higher manganese hydroxide concentrations were primarily associated with has-been aged deposits, whereas the Amazonian aged volcanic regions exhibit comparatively lower manganese hydroxide contents. So based on all the results above, we have constructed a model to explain the formation of manganese hydroxide. We propose that the distribution of manganese hydroxide in Utopia Planitia is closely associated with a vast ancient ocean that likely occurred in the basin. So stage one, during the has-been period, water-rich layers may form through outflow flows or groundwater discharge originating from the southern highlights, leading to the development of the layered subsurface structures detected by the Zhurong rover's ground-penetrating radar. And stage two, a large body of water formed due to mud volcano eruptions, shallow parts of the ancient ocean enriched in dissolved oxygen facilitate manganese oxidation into manganese hydroxide near the surface. And in a deep region of the ocean, manganese could also be oxidized by ClO3. And stage three, as Mars transitions to be more arid, the regression of the ocean continued, promoting ongoing manganese oxidation in the shallow waters. Rapid processes along receding shorelines contribute to the formation of hydrate sulfides. And stage four, by the Amazonian period, Mars had largely dried out, leaving behind manganese hydroxide-rich VBF sediments in Utopia Planitia. However, subsequent volcanic activity from Elysian months buried these deposits under thick lava flows, particularly in the lower lying regions of the basin. And this volcanic resurfacing obscured manganese-rich deposits and introduced variability in manganese hydroxide detection across different geological terrains. And given that the manganese hydroxide precipitation occurred under shallow water conditions, that is what we proposed, is oxidation and accumulation rates could provide valuable constraints on the duration of the aqueous activity. And our estimates suggest that the stable aqueous environments persist in Utopia Planitia for about 0.8 to 1.5 million years. And based on this result, we proposed a minor revision to the timeline of hydrological activity during the has-been period on Mars. We infer that the manganese hydroxide detected by the Zhurong rover formed at the same time with aqueous activity, and this could be the first attempt to directly link the evolution of manganese to the history of water activity on Mars. And here's the conclusions. We have found increase in manganese hydroxides with higher altitudes, and we have found increase in manganese hydroxide on VBF deposits. And we have proposed a model for the evolution of the ancient ocean. And the million-year has-been ocean was proposed based on the deposition rate of manganese hydroxide. And that's all. Thank you for your attention.
We have time for maybe 1 or 2 questions.
Do you hear me? Yeah. So hi, Matteo Losch, IRAP, CNRS. My big question is about all the, I mean, I have many questions, but one of the main questions is, you consider a lot of hypotheses with ocean and so on, but in most other places on Mars, when we see this kind of environment, we actually think about more modern processes like desert varnishes. Have you heard about that?
Varnishes on the rock surface?
Yeah, exactly. Yeah. For example, in Jezero crater, maybe some people can comment, but we see a lot of manganese enrichment that are related to modern processes, basically sometimes maybe atmosphere-rock interactions more than anything related to ocean deposition.
Okay, that's a really good question. And yeah, I have heard that the varnish on the rock surface, and yeah, but the data is limited. You know, the highest resolution figure that we got is the middle line, and it could probably the varnish on the rock, but you have to explain all the results, like the increase in concentrations with higher altitudes, and also why.
Maybe relate that to actually if it's a atmosphere surface relation, maybe it's linked to, it's normal that it's linked to altitude because it's going to affect the stability of water seasonally. So that might be actually linked to altitude for that reason. I work with some of your colleagues on the Zhuang data, and I know there is some period in the past million years of Mars that we know that some short period of time you can condensate water at the surface, and that's obviously linked to altitude, so that might be something you need to look into. And another question also is about the LIPS data. I know for Zhuang you have huge uncertainties. So what are the uncertainties on manganese detection?
Yeah, and another evidence is that you have to explain why the manganese hydroxides are distributed like this, just below the proposed shoreline, and also this one, and why the manganese hydroxide just distributed on the has-been VBF deposits. And we just want to tell the story. I must mean that there's a lot of assumptions. Yeah, we want to tell the story that manganese hydroxides probably are formed in the shallow water environment.
We have just a little more time. Yeah, I agree for the altitude. You need to look into this. And the last question is about your rate of deposition of manganese. How do you calculate it? Are you actually doing chemistry, or it's more just about what are the estimations? I did not have time to see the slide.
Oh, you mean how I calculate the content of manganese?
Yeah, exactly. Yeah. And if do you have any chemistry involved? Because also you have other parameters like the pH of water and the oxygen content of the atmosphere that is going to affect your deposition rate.
Yeah, good question. We calculate the content of manganese basically based on the infrared spectra and the LIPS data. And we construct a data set. A data set contains various content of manganese, like from 0.1 to 15 weight%. Different spectra, and we construct the model based on the data set.
We can speak more after if you want.
Oh, okay.
Thanks.
Yeah.
Let's thank our speaker again. And now we have the last talk of this session by Maxime Pinault and collaborators on recent aqueous alteration in Acidalia planitia.
Okay, great. Good morning again. So for this talk, I will give you some results of our study that was just published last week. So if you want to have a broader view and more detailed results, just check it out. You will have all the information here to go for it. So I will not go into detail. You already know all of that story, but we already know that we have now a lot of indices that permit us to confirm that liquid water had shaped the surface of Mars. We have many geomorphological and mineralogical evidences, especially in the southern terrains of the planet, for aqueous geological processes. And that goes mainly for the Noachian and Hesperian terrains, so that are old and dated back to more than 3 billion years old in age. But for more recent terrains, so especially Amazonian terrains that are mostly located in the northern plains of Mars, we'd have little indication for that chemical aqueous alteration. So looking at the northern plains of Mars has a really great potential to answer key questions regarding the fate of water on Mars, including the presence of lingering subsurface reservoir water that were not lost into space. So probably by looking at these northern plains, we can have a glimpse of potential reservoirs that are buried at depth. So in this context, we conducted a geological survey all over the northern plains, and we focused our efforts on geomorphologies that are thought to have been found through sedimentary volcanism. So those are widespread in the northern plains, and you can see these gray area for sedimentary volcanism. And what is very interesting to note here is that those gray areas are sometimes collocated with the vastistas borealis formation units, so here in blue. That is widespread, the most largest one in the northern plain, and it is of Hesperian age, and it is thought to have been formed through aqueous, potentially sedimentary, oceanic environments. So here the VBF could be kind of a relic or remnant of a past oceanic environment. Okay, it's here. So bit information on sedimentary volcanism. So sedimentary volcanism will occur when you have volatile bearing sediments that will be buried at depth, and if they get compressed or destabilized, heated or whatever, the fluid overpressure will cause the sediment and the fluids to rise to the surface and get erupted, and you will form a sedimentary volcano. So by looking at the surface sediments, we can have an idea of what is going on in the subsurface. And by looking at the surface sediments, we can know the subsurface geology. So on Earth, the best known examples are mud volcanoes. So those big babies can be very gigantic in sizes, like this one in Azerbaijan is about a few kilometers in diameter, 400 meters high. But if you don't have mud or shales that are buried at depth, you will not form mud volcanoes. For example, if you have coarser particles like silts or sands, then you will form sand boils, sand volcanoes, injectites, extrudites, and so on. And those are generally much more smaller on Earth, about a few meters in diameter, for example. Okay, back to Mars. So for the next slides, I will present you some results near the Martian dichotomy. So here in Acidial Planitia, where there are very intriguing geomorphologies that are called the temperate terrains. So yesterday, Frederic gave you some information about these. So those are lobate terrains with light tone curvilinear features that are in fact composed of alignments of pitted cones and mounts. And those terrains are probably late Hesperian and mostly early Amazonian in age. And a lot of people have looked at these and proposed different kinds of formation scenarios, such as explosive volcanism, glacial processes, or periglacial processes, sedimentary volcanism, which is the most favored one, and impact-generated deposits, and probably a mix of all of that. But yet, we don't really know how do these form, essentially because we don't have any mineralogical clue. We don't know the composition of that terrains. But it is no longer the case, as you will see in this presentation and in our publication, because by looking at CRISM orbital data, we have found some hydrated minerals. So here are some examples. You have 4 examples in Acidalia here, where we have the systematic presence of opaline silica. So here in blue, that is always shaded with pitted cones and mounds. And we also have sulfates, polyhydrated sulfates in green, that are either excavated in small impact craters, so you can see that on the top, and on the bottom left corner, you also have sulfates in large mound with hydrated silica at its base. And on the right, you have a very key observation, which is an high-rise image, where you have an impact that gives you a slice into a pitted cone, so that we are able to see the internal structures. So we can see that coarse layering with bottle-rich materials that are bluish and turquoise in color in these high-res images that may indicate that we have some kind of hydration. So silica is not only present at the surface of the cones, but also inside the cones. So the silica, the cones, the sulfates, and the mounds may share the same geological history. So what we can do now is to look at the spectroscopy properties of those materials to better know the mineralogy, especially the silica materials, so then we can better characterize the geological processes that form the cones. So that's what we did. So here on the left, you have a diagram where I plotted some CRISM spectra from the silica-rich pitted cones, and they are compared to terrestrial analogs in black. And what we can see is that the 1.4 and the 1.9 absorptions are really weak, almost absent for some spectra, and we have the 2.2 absorption that is well developed and very asymmetric. And this is indicative of amorphous opaline silica that is polyhydrated and or dehydrated, so silica with minor hydration. And on the right, there is a classification diagram where we compute some spectral criteria that are able to quantify the shape of the 1.4 and 1.9 absorption. And what we can see is that the Acidalia cones are rather associated with the bottom left corner of the diagram. And this is diagnostic of silica that was formed through low temperature processes, probably below 60 Celsius degrees, rather than hydrothermal activity, because we don't have data on the top right corner. So to do a brief summary, we have hydrated silica and pre-hydrated sulfates that are associated with geomorphologies that are reminiscent of sedimentary volcanism. And we have opaline silica that is rather indicative of low temperature processes rather than hydrothermal or magmatic activity. And we don't have any hydrothermal minerals, we don't have mafics, and so on. So all of these observations are highly compatible with the sedimentary volcanism hypothesis, so that we are able to confirm here. And this is very interesting because that means that we have silica-rich and sulfates-rich reservoirs that were buried at depth. So now what we can do is to use the equation from that model to calculate the source depth of the material. So I will not go into the details, but we need the cones elevation using DM data, and we need different assumptions from the density of the surface media, so thin Martian atmosphere or liquid water, and a lot of tested combinations for the embedding units and extruding materials. And overall, we have applied this model to a lot of locations in the Acidalia Planitia region, and we have the same results. So that we are able to reconstruct the subsurface stratigraphy, the geology of the temperate terrains. So here is the main figure of my presentation and our publication, which is a schematic diagram based on all the observation, which is a schematic diagram that reconstructs what could be the geology here of the temperate terrains. So first, near the surface in blue, we have silica-rich reservoirs that are buried several tens of meters deep within the topographic terrains. They get compressed, remobilized, destabilized, and they migrated to the surface to form the pellet cones through sedimentary volcanism. And below, in green, we have sulfate-rich reservoirs that are buried several hundreds of meters deep below the temperate terrains. They also get compressed, remobilized, and so on. And they migrated to the surface across the temperate terrains to form the big sulfate-rich mound that I showed you before. So here, the sulfates are older than silica. And what is very interesting is that those sulfates may originate from deep vastistas borealis layers, probably of Hesperian age. And that means that these sulfates may be kind of indices that we have at least a locally salt-rich aqueous origin for the VBF during the past. So maybe those sulfates could be derived from past evaporitic deposits of potentially oceanic origin, which is pretty much exciting in my opinion. So here's my final slide. So the take-home messages. So we have highlighted the presence of hydrated phases in the print terrains in Acidaria planitia, so silica and sulfates. And this is another indication that we had late-stage, early Amazonian aqueous activity in the northern plains of Mars. And this is the first time that we are able to confirm on Mars the sedimentary volcanism hypothesis using the observation of hydrated minerals. And that means that we have aqueous reservoirs that are buried at depth. And in that place, this has strong implications for the vastistas borealis formation units that could be related to salt-rich oceanic environments. And last points, those silica-rich sedimentary volcanoes are also of major astrobiological relevance because first, they give us a direct access to, at the surface to previously buried materials that were protected from solar and cosmic radiations for most Mars history. And the fact that we have opaline silica is really important too because silica is one of the best minerals to preserve organic mineral molecules over geological timescales. So, looking at these sedimentary volcanoes, especially the silica-rich one, will be of multiple benefits for past water studies and the search for biosignatures at Mars. So, thank you for your attention, and I'd be happy to take any question.
Thank you, Maxime. We have a couple minutes for questions.
The mic is far away. Very nice work. I have a question about the lobes on the submarine terrains. Because outside in the limit, the lobes are always going toward the south, so uphill. And how would you explain this in your scenario?
So you are meaning that kind of stuff?
Yes, exactly.
Right, yeah. It's still difficult for me to understand what are really those large lobate features. So, okay, you told us yesterday about tsunami-like deposits, so that could be. That could be true here, but I'm already thinking about some periglacial processes. Like we have that kind of stuff in Canada that are derived from some moraines, and we have that kind of stuff with the hydrodynamic blowouts, so sedimentary volcanism. But we could have the same features for tsunami deposits at Mars in a cold and muddy environments. Yep.
Definitively, the system here is very complex because there are many things at the same time. So
yeah.
Very nice to have a composition and a mineralogy. So thanks.
Yeah, fortunately, we are going on. And just here we have silica where the temperate terrains are going uphill. So maybe we have that maybe something linked to silica concentrations at the end of the flow. So which is pretty interesting in that case of Tsunami deposits.
Thank you. Let's take one last question.
Manos Kladaris, Purdue University here. I was wondering, the flows that are emanating from these sedimentary volcanoes, they're wet, right? And if that's the case, can you use, like, I don't know, the distance they flowed to constrain, like, the temperature, the ambient temperature at the time? Because I'd imagine if it was super cold, they would kind of chill or freeze.
Yeah, very interesting question. And actually, here in Acidaria planitia, as you can see here, we don't have flow that are spewed from the cones. So we just have, it's like a blowout, a dry blowout. So you just have sediments that are poof, and that's all. But, and it's explained in the paper, we have another example in Utopla planitia. So this is the schematic diagram on the bottom. Here we have a huge mud volcano with flows. And here it's pretty wet. So probably for Acidaria, it's mostly dry-like, but in Utopia, it's wet-like.
Thank you, that's really interesting.
All right, thanks very much. So let's give a round of applause for Maxime and the other speakers. And with this, I don't know, François, any announcement? Okay, so we'll reconvene at 2 o'clock. Thanks, everyone.